Morning, everyone. We will start in about 2 minutes. We are just waiting for a little bit more people. The official starting time is 8:50. So good morning, everyone. Edward will be starting our conference. Thank you, everybody, for accepting this invitation online. Edward, if you want to start.
Can you hear me?
I think we don't hear you very well.
Okay. Well, thank you, everyone. I really like to thank everyone that actually allows to organize this in online form. I mean, we usually, for those that is the first time that participate in this annual meeting, we usually do it in May, the end of May, and is presential. But this time, with all these problems, well, we have to delay it for a couple of months or more than a couple of months, and what doing this way in this online way. I think after we were checking the docs and try to organize the event, we have very interesting contribution for different areas of the particle physics that has been performed somehow in the Mexican community. So I hope you really enjoy the program that we prepare, and also I really hope that soon we could come back and reorganize this in the presential way, because we have several events coming up that probably it would be really nice to join and to try to somehow come back to the way what we used to organize things before. Thank you very much to everyone to joining, and I hope you really enjoyed the agenda.
Thank you, Edward, very much for this introduction. And I think welcome to everybody. So up to now, we have 20, almost 30 people. So I think it's good to start on time. And just to remind you, everybody, that we will have 2 days of a meeting, and we will end our meeting regularly as we have our General Assembly. So I'm trying to see if there is connected Per más Juan. I see Alberto Caramiñana. But let's see, we wait 1 more minute for the next presenter to join us. So we are already started live on YouTube. We have streaming. So please, we recommend all of you to share in the social networks and everything to everybody, so we can have more people attending remotely. So as a general reminder, please, I will request all of you, if you can stay muted. If you have a question, please, you can raise your hand. There is a way on Zoom that you may have a way to raise your hand. And if not, you can put your question on the chat. And if there is enough time, we will give all the questions to the speaker. If not, we will send them to him later, or to her later. See if she or he they will have a way to answer to your questions. So our next speaker is first speaker is a special invitation from is Per más Juan. Will give the status of the process of the muon G-2. I don't see. Are you connected? No, I don't see connected.
Yeah, not yet. I'm checking with him.
Okay, thank you, Pablo. So excellent. So we will give him a couple of minutes, 1 or 2 minutes to have him connected. So we give 1 minute or 2 minutes for the speaker to connect. I will remind you that we have a poster session. This is the first time that we, as a Division of Particles and Fields, we are doing this online connection. Also, we have some elections for the vice president, fully 100% online. And we have our session, poster session later. And this session will be related with, it will be done by a video recorded by each participant of the poster session, and is on YouTube. I will, the link is on our overview of our meeting Indico webpage, and also we will share later in the afternoon the link. So I think we have about 5 presentation already. This is asynchronous. So anytime, please feel when you any break, you can try to start seeing some of the presentation of the posters, because this is asynchronous. So Pablo, any news?
Not yet, sorry.
I think he's already here.
Okay, so Per must. We're still 3 minutes early. Okay. Yes, yes, I agree, Alberto. Thank you. So we still have some time. So we have a full meeting. Everything is very packed. I will request everybody who's presenting that will try to keep the schedule as tight as possible. And if there is time for questions, we will keep time. We will give each speaker full time to present. And at the end, we will keep it. Here we have Pedro Masjuan. Welcome to the meeting. We will just finish.
Good morning.
Good morning and good afternoon for you, I guess, or is.
Thank you. Yeah, you're right.
Okay, so if you feel if you're ready, you may start to present now. So our first invited talk will be given by Pedro Masjuan. He will give the status and prospect of the muon G-2 experiment. So we are waiting for very important news because I think this year this experiment is finishing taking data. And okay, if you may want to start, please, you can share.
Sure.
I will stop sharing.
Yes, of course. So I'm already sharing. Can you see it?
Yes, very good, and we can hear you very well.
Perfect.
You may start. Thank you.
Thank you very much. So before starting, I'd like to say that this is an honor to be here, to be part of this meeting, and to be able to talk about this subject. And also it's a pleasure to present these things because I realized that Mexico had an interesting contribution to the business. So it will be also my pleasure, my honor to remark these contributions to the community. So I'd like to start with this sentence of Arkady Weinstein related to this topic, the anomalous magnetic moment of the muon, when he was saying in his book that the theory trying to explain this anomalous magnetic moment is particle physics in a nutshell. And that's for those who are already in the business, that's why this object keeps us so busy and we find it so attractive. So because there's so many things you have to learn, so many things you can still learn, and so many techniques you have to put on work to understand the object that is really, really appealing. So the outline of the talk will be simple. I like to introduce basically the basic things we are going to discuss for those who are not that close to the business. And then I will give you 2 lines of news about the anomalous magnetic moment. One will be from the theory side and the other one will be from the experiment. And I like also to say that if you like to have a video reference, we gave a lecture in the Cátedra Augusto García González in Sinvestav last year, and you can follow in this link here. You can see for those who are confined or self-confined at home these days and like to have a bit more information about the topic, they are all invited to look at these interesting videos here. So what is the situation? Why are we going to talk about that? Because before starting on the details, no, but just let me tell you, we have an object, a thing we can measure, a thing we can calculate, and it turns out when you look at the difference between what you measure here when you calculate, there's a difference, a discrepancy with these 2 numbers that is nowadays is at the order of 3 to 4 sigma. So this is not enough to claim an evidence of a new physics discovery, but it's already at the edge of that. So it turns out that, as you can see here, those numbers are, nowadays pretty old already. And it has both a theoretical one and the experimental one are relatively old already. So there's a huge effort in both communities, experimental and theoretical communities, to understand better this discrepancy by either doing another experiment or improving the calculations. And as the chairman said at the very beginning, this year, 2020, the new experiment has already collected enough data to release a new number for that A quantity. The actual one, the number that we have, 2006, that you can say is so famous, let me say it this way, that you can even find this number in Wikipedia. No? So this result here with an error of 6, 10 to the minus 10, it comes back from an experiment performed at Brookhaven, 2006. And for those who are in the audience, I'd like to, I mean, if you don't mind, I'd like to ask you as a sort of homework during the talk, to keep in mind this number 6, 10 to the minus 10, okay? Or 63 or 60, if you like, 10 to the minus 11, just to keep it. Well, this is going to be our focus number for all the talk. As you can see, the theoretical, the standard model, there's a table here. The standard model, it has an error of around 6, 10 to the minus 10 as well. So when you combine both 6 and 6, you will get around 8, 10 to the minus 10 as a combined error. So this brings this 3 to 4 sigma. Okay. So as I said, there's a new experiment. This new experiment is running now at Fermilab. You can find here the web page. They already performed the first run and part of the run 2. And run 1 data is already on tape, analyzed, and by different groups, and will come in news later on. So as I said, so we have this discrepancy here, 3 to 4 sigma. So we like to reduce that number or increase it to see whether there's a new physics or not here. So the goal then would be, in practice, to reduce the experimental error by 6 down to, say, a factor 4, down to 1.6. And if the theory wants to, say, keep the experimental effort, must try to do the same. So reduce the theoretical calculation error down to 1.6 as well. So having said that, this is our goals, try to reduce experimental errors, theoretical errors. I like to introduce what are we talking about? What is this so interesting object? Well, it turns out that the object itself is pretty well known, and from actually many years, and is the Landé factor G that appears when you have a particle that has spin, an electrical charge, and you put it in a magnetic field, as you can see in this illustration here in the right corner. And you see that because of the having spin, the magnetic field feels that this particle is like a magnet. So there's a magnetic moment appears. The strength of this magnetic moment, this interaction between this magnetic field and the spin of the particle, the magnitude is proportional to this factor G, the Landé factor, that can be calculated, say, for particles of spin 1/2, can be calculated from Dirac theory, and you get, as a result, G being equal to. But it turns out that we know that the ultimate theory is not the Dirac theory, but you have to take into account the radiative corrections to that. So you have to use quantum field theory to do that. And as soon as you do that, you realize that G is not actually 2, it's slightly larger than 2. So the deviation from this Dirac value is what we call the anomalous magnetic moment. It's anomalous not because you are seeing an anomaly, but it's because you are seeing a deviation from the Dirac theory. That already tells you that this name anomalous comes from very early times, where they were in this bypass between the Dirac theory and the first quantum field theory that were appearing. So we define an object A, called A, as the departure from G minus 2. So in the Dirac theory, A is exactly 0, but what we are going to say that A is not 0. In particular, is because of this first correction here, this Feynman diagram. You can see here, this is the first loop correction, where you have your line here would be, the solid line would be your spin 1/2 particle. You have the magnetic field in blue, and then you will have a radiative correction here contributing to A And for example, at the leading order, this particular diagram will give you a correction which is already 10 to the minus 3. So it's at the per mil level. So if you can measure this object at the per mil level, you will start seeing relative corrections to that. And this is our business. So the precision we have nowadays is 10 to the minus 10, not 10 to the minus 3. You can see the effort from the experimental community to reach this precision, amazing, 10 to the minus 10 in this very small object. And I'd like to present now what are the theory efforts to reduce the theoretical errors, as I commented at the very beginning. So the theory efforts go under the writing of a white paper that has been an enterprise for the last, say, 3 years or so. And we, 3 weeks ago, managed to upload this white paper into the archive. This is the white paper called The Anomalous Magnetic Moment of the Muon in the Standard Model. And I put in red say, Mexican collaborators to this paper. So as you can see, the Pablo Roch and Bashir also, in their collaboration, contributed to this paper. And you will see later on that there was also numbers that we are collecting in the white paper come from the Mexican community. So this is how it looks like. There's a lot of authors. That was a success. Not all of the people in the community is here, but this, as a first attempt, as a first white paper, managed to include many authors. Yeah, so trying to reach a large consensus on what is the standard model value. And this is a part of the executive summary of this white paper, which is around 200 pages long and collects all the contributions that one has to include from the theory side to account for this anomalous magnetic moment. As you can see, there's a long list of contributions. And I should say that the goal of the white paper was not only collecting, but also updating all the different contributions. So all the numbers are now revised. And actually few are even new. And here you can see again in red how would the Mexican contributions appear here in this reference here in one of those. And I unfortunately have also to say that even though all these efforts that theory community put, we didn't manage to go down to the goal of say in these units 10 to the minus 11, 16. So we didn't manage to reach the 16, but we stopped, say, we find we couldn't reach, so we could only reach this 4 or 43 in 10 to the minus 11. And I like to comment what happened here, what are the discrepancies, which is a way to say what is the work to do now to reach our goal. So this is the anomalous magnetic moment from the standard model. This is our object, the theory object here, a mu. And when you look at a mu, you calculate it in the following way. So you split from that object all the different contributions appearing from the different sectors of the standard model. So you will have, of course, a QED part. You can already anticipate that because the first loop I put, it was just purely QED loop. It was just a photon running in a loop. So this goes into the QED part. But it turns out that since you are needing that precision, that high precision to account to counterpart experimental result, it will happen that your photon here running will at some point eventually see, for example, quarks. So you will have to introduce as well QCD in the business, even though the contribution is very small. And also at some point, the electroweak sector via, for example, a Z exchange or even the Higgs would contribute. And this is always because of the precision you are reaching. So then you have to calculate the different terms, and then you sum up to reach the standard model prediction I was commenting before. So nowadays, with the all 2006 Brookhaven result from the experimental community, the current, say today, discrepancy between theory and experiment is at the order of 3.7 sigma. Okay. So just let me briefly comment on the different parts. So QED is the most largely contributing, by far in 99.99% comes from QED, and this is thanks to the complete 5-loop result. This was an enormous task, as you can, well, I mean, I don't know if someone can imagine that. I cannot imagine that. I was super surprised when I saw the result and the enormous work put on this and to get this number. The example is, for example, these are the topologies one has to calculate. There are, at the level of 5-loop, there are more than 12,000 diagrams, and then you have to develop methods and computational methods to account for all these integrals you have to run here. So it's an enormous work. You know? Fortunately, on top, there are also analytical checks at the for-loop level, contrasting and confronting these results. So everything seems to be very stable from the QED part. I remark that because, well, later on at the very end, we'll have to come back to this point here. The second contribution is the electroweak part. This is a small contribution. If you remember, the error in this 10 to the minus 10 nowadays is around 60 in this unit. So the electroweak, even though small, is very important to understand the discrepancy theory and experiment. So it's large enough with respect of the current errors. And this is reached at the two-loop level, and the error was lately reduced as soon as the Higgs boson was measured. So imagine how was the situation, how precise we are discussing these objects, that the largest error source for the electroweak contribution at the two-loop was the uncertainty or the unknown Higgs mass. So as soon as that was measured, this error was reduced, and now it is pretty stable, this number. So the largest theoretical error comes from a QCD, or the fact that the photon can see quarks. This brought the largest uncertainty on this result. And that was the focus for the last years from the theory community, trying to reduce, when they were saying, I like to reduce this 6, 10 to the minus 10 from the theory side, the focus was put on the QCD part. And this is a plot, we'll later on explain a bit more, but this is just to show you that indeed this progress translates into the fact that, for example, these different determinations you hear are scattered. This is chronologically going down. So here down are the newest results. They agree much better among each other. So the scatter has reduced, and this provides smaller errors. So this object is very complicated. This QCD part is very complicated, and it has two different terms. The dominant one is called hadronic vacuum polarization. And it's the fact, as I was mentioning before, that as soon as you have a photon in a loop, this photon has a Fock state, has a probability to produce electrically charged particles, in particular, quark and anti-quark. And this can be done at whatever energy running in this loop. So then you have a problem. You would like to calculate this integral, and you like to calculate how this photon transforms into quark and anti-quark, but being very low energetic, but also being very high energetic. And we don't have such a theory to go to calculate what is the relation between a photon and two quarks, very low energetic and very high energetic. Because QCD in particular can be used at a very high energy tail, and so we cannot use perturbative QCD for the full loop. So you have to find another way, and the other way comes from using the optical theorem to relate the diagram you like to calculate with something you can measure. That is actually the hadronic cross section between electron, positron, and hadrons. So this is the hadron production, for which we have a lot of data, experimental data, as you can see here in the plot. And then to account for this hadronic contribution to the G minus, to the anomalous magnetic moment, you have to do this integral, where you have here just a QED kernel, and here you have your experimental data. Fortunately enough, both the kernel and the cross-section are dominated at low energies, as you can see here. So this low energy region is the one that is the most important. So you don't need to have data up to infinity, if you like, even though you have to integrate up to infinity, as you can see here. So at the end of the day, You can see here the quality of the data is amazing. There's many experimental collaborations contributing to these cross sections. So you can perform your integrals on the data, and you do it because the cross section is an inclusive process. You do it channel by channel. All the hadronic channels you produce in a plus and minus a collision, and then you sum them, all of them up. There are more than 30 right now nowadays. And of course, the channel with the lightest hadrons dominate, as you can see here. So you sum up, and you can see here the pie of the contributions of the different energy regions. No? So this is the energy, the GeV energy. And you can see that, say, up to 2 GeV, you have 95% of the integral already saturated. While the error is slightly different, the percentage is slightly different, and you have to be a bit more careful how to define it. So at the end of the day, you can calculate by looking at the data with the newest possible data, and there's a lot of efforts from the experimental colleagues to providing precise data. So you put this data into your code and your integrals, and these are your numbers. No, you have to take into account I was talking only at the leading order, but then you can have extra photons in the muon legs, or a second loop, and then you have to calculate all those things. You have to sum up, and this is the number. And this is one of the collaborations doing that summary of the results. And what happens is that when you compare these two different ways to sum up these integrals, you find a slightly difference. And this is very nice that in the collaboration, they provided the difference between the two numbers. So you can see here by the different channels, you'll see that there are still slightly deviations in the particular channel, even though in the sum of them is very similar, and you see perfect agreement on the plot I showed you before. When you go to the individual channels, there are still deviations. So when you take into account that the fact that when you compare the numbers, these differences accumulate, you find out that the final error is 40, even though you wouldn't ascribe such a difference by just looking at the plot. So there are still work to do. So remember, our goal was to compare with the experimental goal is 16. And since in the standard model, everything sums up, all the different pieces sums up, we have to reach an error of 16, at least for each of the contributions. So we are still slightly far away from that. And there's at least still work to do here. There's also I was commenting now on how the standard approach has been pursued by looking at this dispersion relation and the optical theorem to relate the diagram you like to calculate with experimental data. But there's another way to perform this calculation, and it's through a lattice simulation. A lattice provides as well different results for the same quantity. You can see here, I was just talking about these two red numbers here, that they are showing a difference between the theory and the experimental result. And this is what would be the window, the scissor for the new physics. But it seems that the lattice simulations are not so optimistic or pessimistic. This is depending on the viewpoint. But they are finding larger values, larger contributions for this vacuum polarization from the QCD, the leading order QCD part. So if we would be trusting exclusively, say, the lattice simulations, you would say that there's no such a discrepancy any longer. So there's now a conflict between the two results, apparently, because they are large. And so we have to wait a bit more on how the things evolves. The surprise thing, and this couldn't enter to the white paper, is that the very recent update of this lattice collaboration is finding a very precise result, confirming basically their previous one, and so in a way confirming that there are no new physics any longer in the G-2. But I have to say immediately that this is only a leading order calculation. And then you will have to do a next to leading order calculation and a next to leading order calculation. And we know that the next one, the next to leading order is going to be negative. So whatever happens now, this number, I hope, will go to the left and still giving space for this in physics. But this is just my guess and my wish. So this is something to stay tuned about. The other part of the progress comes from another contribution, which is even smaller, which is a order alpha to the cube. Well, the previous one was alpha, order alpha, so this is alpha to the cube, so it's much smaller. And it goes under the name of hadronic light by light. This is this sort of diagram here that is a very difficult to calculate, even though it's a small part, was contributing with a very large error because of the difficulty you have to find when trying to calculate it. And the problem goes because you have here a QCD result, QCD elements here, degrees of freedom, linked by different photons that can have different energies. So you have a multi-scale problem. And if we already don't know how to solve QCD at all energies, what happens if you have many different energies involved? So no way to calculate it from first principles. So you have today, and that was the traditional point of view, try to use, say, low energy models to account for the different pieces. Then you would split whatever you have to calculate, you split it in terms, in pieces that you will, at the end of the day, sum up, pieces that you believe you can calculate individually. And that was this the traditional effort. So the main progress here is that we have a slightly different way to proceed, theoretical way, that is using dispersion relations to split up this diagram into the pieces that you have to sum. And by using quantum field theory tools, we now know how to do this sum coherently, trying to avoid any possible double counting. So for the dominant piece, that is going to be when you have this object with a pi zero running, propagating here, you have to solve this two-loop diagram. And here in blue, I show you what is called the form factor, the pi zero form factor. This is an object that you don't know how to calculate at full kinematics. So you have to rely on experimental data. And this is the path to go nowadays. And that's the philosophy followed by the white paper. And then in particular, by doing so, you find that the contributions of the hadronic light by light go under the pion, eta, and eta prime, axial contributions, a pi scattering, and so on. And I would like to show that this is I'm proud of that. That's why I mark it. Sorry for that. This is my own contribution to this business. And here we observe as well a part of the, say, Mexican contribution under the authorship of Pablo Roche. So these are the results that nowadays we have in the white paper for the light by light. And as you see here, the error is 19. Well, our goal was 16. We have to be proud. And the result, beyond being proud of that, so we try to reach this goal of the error, we are also learning that using experimental data tells us that these objects, the transition form factor, are more important than expected. So when you have to model this object, you have to be careful to satisfy or to comply with experimental data that all these the collaborations are providing. And also another part which was sort of missing in the all analysis is the systematic error that you have to use in order to comply with the different kinematic regimes with your model or with the object you are putting as a form factor. So those things we learn and we know how to do now. And then on top, there's a nice confirmation from Lattice. Lattice can also simulate the hadronic light by light. And even though the errors are large, well, they are in the ballpark. But beyond being optimistic on that, I have to say that there is still there's a contrast with ballpark estimates, previous ballpark estimates using perturbed QCD quark loop. So there's a completely different method to account for a ballpark for this quantity. And all the different ballparks, let me remark here the work of Erle and Toledo Sanchez in 2006, they were finding sort of larger contributions for this light by light. So, well, okay, within errors, we are there in the ballpark, but you see that they tend to be to provide larger results. So it may happen that there is still something to understand, especially that's now my opinion, the link between low and high energies. So how the connection between these two regimes are performed, there are still discussions ongoing and something to learn here. Okay, so having said that, I'd like to move very briefly to the experimental side and to tell you what is how do you measure this object. So I was very detailed on how to calculate it, and now I'd like to show you how to measure it and what are the prospects. So to measure the G-2, the anomalous magnetic moment of the muon, you have a storage ring. This is a large magnet, 15-meter diameter. Is a unique piece, very huge, as you can imagine, and you inject muons, pretty energetic, inside of that. You have a very strong magnetic field, almost 1.5 Tesla, and you allow these muons to run inside your magnet. Okay, since they are very boosted, their effective life is going to be very large, so you can have very nice statistics. And the idea is that then by comparing these two frequencies, see the time that a muon needs to run the full perimeter of your ring compared to the relation between the spin and the linear momentum, how the spin is precessing around the linear momentum. You compare these two times, you will get the anomalous magnetic moment. And the reason is simply because of the having a anomalous, so this magnetic moment. As soon as you have your magnetic field, the spin will feel it and will start precessing around the momentum of the muon. So you can compare these two frequencies. Here you see the area, and then you find directly, by comparing these two frequencies, you find directly A. So, but for that, you have to know the angle between the momentum, the linear momentum, and the spin. How you do that? Because the muons are inside your ring. Well, the fact that the muon decays into in this case, on a positron, the anti-muon decays into a positron, already gives you the hint on what is the angle between the momentum and the spin. So you have to just capture these positrons, and you do that by using calorimeters that provide you the time, the energy release, and then the angle. And from that, you get these very nice plots here, sorry, on the decays of these muons. And then the thing you have to do is to fit the sinusoidal signal to get the frequency of the anomalous magnetic moment. Actually, there are subtleties here, as you can imagine, and particularly related to the magnetic field. You like to have a precision of 10 to the minus 10 in your result, so you would be obliged to have a measurement or an homogeneity of the magnetic field at the same precision. So that's impossible. So what you do is you use the free proton precision frequency to get rid of the magnetic field in your equations, and then to reach a much preciser result. And that's what you do in the experiment. Okay. So with this technique, that's how you the Brookhaven collaboration reached the result I was coming before, 610 to the minus 10. This result comes from combining two different muon and anti-muon channels. So you perform the experiment for both, and then you combine the errors, assuming the CPT, so that both channels must give you the same result, and that's why you reach at this precision. So this is an historical chart on how the things evolved for this experiment. Starting, the precision era started at CERN in the 60s, and then moved the experiment to the Brookhaven, and that's our current number. And the forthcoming experiment tries to reach this 1.6 10 to the minus 10. Okay, and then by satisfying this goal, they moved the magnet from Brookhaven to Fermilab. Around, that was 6-7 years ago already. They set up all the experiment, calibrated, and nowadays, as you can see in this chart, we are here. They are already finishing run 2 actually of the data, and the plan of run 3 for this year is under the schedule. So nowadays, the Run1 data is already on tape, analyzed by different groups in a blind analysis. Most of the systematic errors are well under control, and we expect all that by the end of the year, say in a few months.
Sorry, Pierre, you have 10 minutes?
I'm perfect on time. Thank you. So by the end of the year, we'll have this release of the first publication. I have to say that the Run1 has the same sort of statistics as the Brookhaven. So it's the equivalent set of data. So you would expect to have similar final error. So not yet the final goal, that the final goal is going to be reached by, say, 2022, when the 5th run is done. But this year we should have similar results, similar experimental result as we already have by the Brookhaven experiment. So I'm going to the conclusions, and I like to share with you a pessimist view. Sorry. Why I'm pessimist? Because we have been discussing, like, for these 40 previous pages about the anomalous magnetic moment of the muon. But all other leptons have as well anomalous magnetic moment, and in particular, the electron also have it. And it turns out that recently, a new measurement of the electromagnetic coupling using a mass spectrometer, sorry, for the cesium cavity, they found a very precise result for the alpha. And then by plugging in this experimental result into your QED calculation for the anomalous magnetic moment of the electron and comparing with the experimental result, you find a discrepancy on the electron side that is actually negative, not positive. So this is a pessimist view. I say that because now we have to solve both problems, but being the electron G-2 very much QED driven, whatever you need to solve it is going to spoil the anomalous magnetic moment of the muon. And this is the idea. No? So you can see that whatever genetic contributions of new physics you would put, you are going, if you want to save or you want to solve the G-2 of the muon, you like to have a positive, you can see here, a positive contribution. While for the electron, you would like to have a negative one. So either you solve one or you solve the other. And because of being much more theoretically safe, the electron counterpart, you are much sure going to spoil the muon. So there's a pretty pessimist. On top, there's a second pessimist argument from my side, is that at the Fermilab, they are now running with anti-muons. So when they say we are going to emulate, to confront the previous Brookhaven result with the similar error, what they are saying is that they want to compare with the one at Brookhaven that had the same sort of muon. And actually it turns out that when you look at the different channels, one of those is smaller, closer to the standard model. So if we are going to compare with the anti-muon result, if the Fermilab gets the same central value with the reduced error, just by having the same central value, we are going to have a discrepancy that is smaller between the standard model and the experiment. And on top, there's the idea of perfect. There's the problem of whether the theory number is well under control or not, in view of the recent Larry's results. But I don't want to stop here in the pessimist view. There's an optimist view as well, and it goes by the fact that there's a real proposal, a formal proposal to build up a completely different setup experiment using now cold muons, not so energetic muons, in Japan at J-Park, where you are going to have a LINAC and a penning trap, for which you will have a lot of precision with a very strong magnetic field to measure the precession of the muon. And this is an excellent news, and I'm very much optimistic because whatever happens with the Fermilab experiment, you will be forced to have a second different experimental result to be sure that what is happening, what is saying the Fermilab is going to be the truth. And this brings me to my conclusions, that this is just, that's what I wanted to say. I just wanted to expose that there's new data was required to get to understand the discrepancy theory experiment, and we have soon new results from the Fermilab, but also this JPark initiative. In my opinion, it may happen that the theory errors are still underestimated, even though this huge effort on the white paper that all the part of the community put to understand better these numbers. And it seems that lattice is demonstrating actually that by this discrepancy in the vacuum polarization. But there are other issues, for example, more theoretical in the part of the light by light, as I was saying before, that maybe how to link low and high energy are not that clear. No? I also like to say, just I'm done, that the new physics effects are constrained by LLC. So there's it may happen that if new physics are there, we'll not be able to explain fully the anomaly, because the anomaly is already, the one that we are seeing is large enough and is already constrained by the LHC. But then it would be nice also to explore synergies between these G-2 and favor anomalies in BTKs. So the summary is that, well, the news will come at the end of the year, and I hope the discrepancy will still be alive. So thank you for your time, and we'll be glad to have questions.
Yes, Bert, thank you very much. I think it's very exciting time. So I think this is one of these experiments in theory where both of them are pushing very hard for precision measurements, and you have, it's not the job of a single person, it's in both cases. And this is a very, very excellent summary. I think we have one question from Pablo Roig. So Pablo, if you want to ask, please.
Yes, thank you very much, Pera, for this excellent overview. It was so great that I will ask you about a few things that you didn't have time to mention.
Okay.
So yeah, okay. So one is about the simultaneous presence of both anomalies in the electron and in the muon. So in addition of this different sign that you emphasize, then also if you look at them from the EFT perspective, taking into account that for heavy new physics, the effect scales with the lepton mass square, then the new physics scales needed for the electron and the muon are quite different. So this is another indication that maybe at least one of them is not there, right?
That's very true.
And then I would like to ask you the same question that was asked to Aida in the Fermilab seminar presenting the white paper. So you highlighted very clearly the new result by BMW collaboration that seems to point to no new physics with very, very reduced error despite being a lattice computation. So you mentioned that this is leading order and then there will be corrections to it. I don't know how these corrections are in lattice. If they were as if they are on the analytic side, I wouldn't expect that this change so much the result, but I don't know in lattice, so maybe you can comment on this as a sub-question. But the main question is what happens if in the end the lattice confirms the BMWC result with this uncertainty? And then the people using data also confirm the trend that are shown in the bottom part of the plot. And also another sub-question there on this particular side, you mentioned these differences by mode, but in addition to this, focusing on the pi mode that dominates, there are big discrepancies in the shape of the distribution between the two most precise experiments, Babar and Chloe. And in relation to this, we eagerly hope a measurement at Bell 2 of this E plus E minus to pi plus pi minus that maybe can help understand this issue. So this was my main question, and some sub-questions, if you can say something about this, please.
Yeah, thank you, Pablo. You're very, very kind with your words. I try to catch up all the questions. So let me start with the first one. That's very interesting. If I have to bet between electron and muon, despite all the work we have, all of us put on the muon, I would definitely bet on the electron. So why is that? Because the theoretical calculations very clean, is much more dominated by QED that we have very much under control. And actually, when you look at the discrepancy theory and experiment in the electron part, the standard model has almost no contribution to the error. So unless we clarify that point, or the electron is going to dominate. So second part, about this plot here I'm showing concerning the difference between lattice and the dispersion relation, the data-driven results. Oh, that's a very difficult thing. And I would like to be say clear here. Both results here are black boxes. It's not easy either to understand how the lattice results are coming out, but it's also very difficult to understand how the results are coming out. So it's not a work of a one afternoon, as you can imagine. So if there are systematic errors are underestimated, which may happen in both sides, and that would be my own conclusion, it's difficult to see. So I agree with you that I don't know how the nextoning order in the lattice A result would appear, but I guess it will also be negative. So you will go say a bit to the left. But say that this result of the lattice is confirmed, this would be very sad, and I tell you why. Because if say the lattice confirms that there's no new physics, we all will lost interest on this object. But we will leave for the next generation the question why the two methods are so different. So nowadays, the difference between these two results is around 3 sigma. And this is a large deviation for two different results talking about the same object. But if that doesn't involve new physics, I fear that we will lose interest on that. So still hope that something will come out and there will be some systematic error. Let me say, as you were nicely pointing out, that this situation that I'm showing here could also be related with your first question about the difference between the muon and the electron. If you want to explain the electron, you would need a scale of new physics much larger. So that would impact on the muon much less, and then you really don't need that this large discrepancy in the muon to have still new physics. So it may happen that the current discrepancy is by far too large, and after the new experiment and after the say new theory results, the discrepancy will be smaller, and that will cope with the one from the electron. So that's, in my opinion, it may happen, and still both results are suffering by having low underestimated systematic errors. And I'm just finishing concerning the results of Bell 2. You are right. There's another very interesting thing, that is this object that I have here in this plot is the vacuum polarization. This thing also enters into the running of the alpha electromagnetic, for example, from low energy to the Z pole. So LHC physics are also seeing these sort of effects. And then you would like to contrast what you are here, I'm showing here with for example, the measurement of the Z mass at the Z pole. And that result, which is also very precise and is completely a different energy scale, is also telling you how these discrepancies are. And you would arrive to the conclusion that if there has to be a discrepancy, it must be at very low energies. And for that, say, the tail of the raw meson, but on the low energy part of the tail will be definitely very important to understand. And I'm very much sure that Bell 2 will have their work on that business, but definitely. And that's, in my opinion, that's the thing we have to do now. So understand how from the threshold of 2 pints up to the raw peak, this data is, and what discrepancy one would be able to include there to account for this, for the discrepancy between these results here.
Thank you very much.
Thank you very much, Per. We are just 2 minutes late, and sorry, we have another question. I think if you may want to put it on the chat, and we can later send it to the speaker. So we really thank you very much for this very clear presentation of both theory and experiment. And the G part for the future, I think, starts in 2024 or something. So it's very interesting. Thank you very much for your time and your contribution to this meeting. Thank you very much. So if you may stop sharing. And
yes,
our next speaker is...
Yes? It was my pleasure. Thank you. Thank you very much. It was really my pleasure and my honor. Thank you.
Thank you. It was honor for us. Thank you. So Alberto Caramiñana, if you want, you may want to start sharing. You are next. Alberto will talk about the Hawk sky survey at the highest photon energies. I think some very interesting news we will receive from this experiment, which is in Mexico. Thank you very much. You may start. Alberto, you may be muted. We cannot hear you.
Yes, I was muted. Sorry.
You can start.
Okay, thank you very much. It's a pleasure to come here from the astroparticle community and to talk a little bit about what we're detecting here in Mexico with the Hawk Gamma Ray Observatory. So in particular, focusing into the highest photon energies. So most of you know what is Hawk. Hawk is for High Altitude Water Cherenkov. It's a gamma ray observatory. You can see it here. You can even see its new outriggers around it. And we're next to the Gran Telescopio Milimétrico Alfonso Serrano, and we're at 4,100 meters altitude. Hawk is a multinational collaboration of physicists, astrophysicists, geophysicists, and we're working with this experiment in Puebla at 19 degrees north latitude, about 100 kilometers east of where I'm talking to you. It's a wide field of view. We can see about 15% of the sky permanently. It's continuously observing the sky. It's observing right now. And it covers 2/3 of the sky in one survey, in one sidereal day. And we work basically in the TeV energy range. We're optimal at 7 TeV, but our response is also pretty good at higher energies, up to 100 TeV, as I will present here. This is the last presential meeting of the Hawk collaboration in Puebla, and the collaboration, which was made of physicists in Mexico and the United States, now has participation of about 10, 12 countries in Europe, Latin America, and Asia also. So the observatory is a form of 300 water Cherenkov tanks, 5 meters tall, 7.2 meters diameter. Basically, we use water, Cherenkov light in water to detect secondary particles created in high energy cascades, mostly hadrons, protons, and other nuclei, but we can reject them very efficiently to detect gamma rays. So I'm presenting you, we have close to 5 years of data, 15,000 days of light data. So that's about 92% of the timing here. Once you reject bad quality data and short periods where we off. Particular, we're working and we're about to send to publication the third Hawk catalog, and we're also finishing the AGN survey, which I'm not talking here. So we are detecting sources close to 100 TeV. These sources, some are powered by hadronic mechanisms, some leptonic. And of course, one of the questions we want to respond is the source of the cosmic rays in our galaxy. And of course, that needs hadronic accelerators in here. So since very long time ago, or 60 years, Fermi proposed that shocks in the galaxy, he in fact demonstrated that shocks produce powered low spectra of particles, like we observe in the cosmic rays, and expanding supernova like this one from the year 10,006. So it's been expanding 1,000 years in their shock with interstellar medium can produce a large number of cosmic rays. And in fact, the idea is that if you have one supernova every 30 years, and you put about 3% of this energy of this supernova every 30 years, you can satisfy the requirements for the production of the cosmic rays, their energy density in our galaxy. So supernova is one of the sources we are looking here. So this is the sky map that we have. It's a very clean sky map. All this is the galactic plane. This is in celestial coordinates, so this is more or less latitude. Here is latitude 19. So this is the galactic plane. We don't reach the galactic center, which is pretty much here with my hand. And then the galactic plane comes up here. And here, this is the anti-center where we have the Crab Nebula and other objects. I'll talk shortly in the opposite direction. That's looking opposite to the center of the galaxy. And then we have some AGNs, Markarian 421 and Markarian 501, among other AGN in here. So zoom into this region and in galactic coordinates. So we have the Crab Nebula, a very, very bright spot. And the Crab Nebula, even though it was supernova about 950 years ago, in fact, what we have is a pulsar wind nebula. That is, the pulsar is just exciting the environment just next to it. And that's where the high energy particles and gamma rays are being produced. But in the same region, we have several other objects. The Geminga pulsar is located here, and we have kind of a blob of emission. There is these two are nearby, 200 parsecs away, pulsars B0656 plus 14 monogem. And here we have a supernova remnant. This is a shell supernova remnant, one kind of textbook emitter of what Fermi would have expected. And here we have this new object, which seems to be what we call a TV halo. If you smooth this, basically you can see that around these objects, these TV halos, we have extended emission that was shown by Hogg, and also in this case. So right now, the idea has been growing in the last 3-4 years since the observations and the publication of the results by Geming and Monogem, that you have kind of a evolution where you have a pulsar here accelerating particles which are confined in the pulsar wind nebula. If you leave enough time, this is the youngest of the objects, it's only the pulsar wind nebula, then you get a halo of electrons, positrons that are escaping and making emission, which can be extended up to 10 parsecs or 30 light years. And in some cases, you have the shell supernova remnant, that is a hadronic accelerator going and expanding up, like in the case of IC443. So it's very nice that in this region of the galactic anticenter, we can see all these three types of accelerators that we are finding in our galaxy. Okay, so here I missed a couple of equations. Yeah. Okay, so basically pulsars have the power, they can produce 10 to the 38. If you remember, you need 10 to the 40 ergs per second in particles to have the emission from our galaxy. They have the magnetic fields, and they can, here it's missing the equation, they can accelerate particles to easily 10 to the 16 electron volts. And they keep producing these for close to 10,000 years, 20,000 years, more or less. So most of the objects that we are seeing are leptonic emitters, that is pulsar wind nebula or these TV halos. So what about hadronic cosmic rays? So can we show that we are seeing hadronic production, just a sort of cosmic rays we observe on Earth? So in fact, leptons, in order to produce, so electrons, in order to produce gamma rays, they need to use the inverse Compton scattering. And that is limited by the Klein-Nishina cross-section, when the product of the energy of the electron and the photon that is to be scattered is order of 1 in units of mc squared with md electron mass. So basically, if you to produce photons of energy close to 100 TeV, when this gamma is of order 10 to the 8, basically you need this omega to be 10 to minus 8 in units of the electron rest mass. So that's only the cosmic ray background, cosmic microwave background, the 3 Kelvin background that can provide these low energy photons. So we know very well how to model this. So in fact, if you see sources that get close to 100 TeV, then you are most likely to be seeing hadrons emitters. The other thing, and we're working on that, we don't have results to show right now, is trying to also search for neutrino emission. So Hawk works very close with IceCube in order to try to find coincident TeV gamma rays with neutrinos. So where are these hadronic accelerators? This is the galactic plane. This is basically galactic center would be here to my right, and this is in galactic longitude, almost 90 degrees going from the galactic ridge, 1908, this very bright region, and at the end, the Cygnus region of high mass star formation. So, in fact, at the latitude of 100, so 20 degrees further north, in this case, from here, we have found this object. This is just sent to the archive. It's accepted by astrophysical journal letters, which is next to the Boomerang Pulsar Nebula, but in fact, this is a larger association that we can, this gamma ray emission in red, we can associate to the supernova remnant. This is at 61 degrees north, so it's a hard target for Hawk. It's inclined, so we have to observe at large zenith angle. So only showers of high energy can get to us. So this is the fit. This is our data. So we're finding emission from 40 TeV to 100 TeV in this shell supernova remnant. So this is, we believe, a pretty solid argumentation in favor of hadronic cosmic ray production. And in fact, when we take our galactic plane, so going from close to the galactic center to the Cygnus region, we can cut and try to see our highest energy sources. So we've done cuts at 56 TeV, 100 TeV, and even 177 TeV. So this was published last year, the reference comes later. And we have like 8 sources that you can see, 9 sources that you can see above 56 TeV. 3 of them, one in Cygnus region, emit of more than 100 TeV photons, and this one up to 177. And these are the highest energy photons one has observed from the sky, bearing in mind that Auger has only put upper limits in photon detection. So these sources are the hardest sources we have detected so far in the sky. So
5 minutes.
Yeah, this is 1825, 1908, and then the Cygnus source at 2019. So you can see here the spectra of these 3 sources. This is a physics review letter, very recent. And basically, if you put a question on with how far are you seeing in energy these photons from these objects, you can put 95% limits on the highest energy photon of up to 244 TeV for the black source 8025 fairly along the galactic ridge, and also this one 1908 or 1907 in this case, up to 200 TeV, or if you're more conservative, 3 sigma limits on 158 TeV. So people like Humberto Martinez have worked on setting limits for Lorentz invariants. Basically, they assume that the dispersion relation is not satisfied, so they put an extra coefficient here. Here I'm missing a term, but basically you can relate these alpha n, depending on the degree of the violation of the Lorentz invariance, to energy scale of invariance. And this goes for n equals 0, n equal 1, n equal 2 in this series. So basically, this energy elif in the case the energy you can set for n equal 1 or higher. These are bounds that have been from other observations of the Crab and gamma ray burst. And this is combining the Hawk sources. And this is a work where Humberto Martinez Huerta has worked very, very hard to get these limits on a scale of over 10 to the 31 EV for violations of the first degree, and 10 to the 24 degrees. That's the degree of violation that Lorentz invariance would have in this case, in particular for the hardest of the source. You get to 10 to the 24 EV as the lower bound on the particle energy. So that's just, I go to my summary. So we've been operating quite successfully for 5 years. We have detected tens of sources. In fact, the third catalog will have 65 sources, most of them along the galactic plane. And we see pulsar wind nebula, TeV halos, which are leptonic or presumed leptonic sources, and supernova remnants, hadronic. Didn't have time, but also the star formation region Cygnus OB2 seems to be producing hadrons through stellar winds, collision of stellar wind shocks in there. And we have detected gamma ray sources above 100 TeV, and these are likely hadronic accelerators. And at the same time, these sources provide the best current astrophysical limits on potential violation of the Lorentz invariance. And hopefully sooner rather than later, I'll be able to tell you more about the work that some people are doing at Hawk of coincidences between ice cube neutrinos and Hawk emission along the galactic plane. So that's it from me. Thank you.
Thank you very much, Alberto. So we have still 3 or 4 minutes for questions now. So let me check if we have any question on YouTube. So in the meanwhile, I will ask you. I mean, we are trying to make one question per people. So I have plenty of questions. It is very interesting experimental detector in Mexico of high quality. So I will ask you the future. What do you expect for the next 5, 10 years or more for the Hawk Mexican and other international experiments?
Yeah, so in principle, we're operating 10 years. So that's what we have permit with Semarnat. And we have funding from the National Science Foundation until 2023. So we're certain 3 years and probably 5 years. We're not sure if we'll be taking data longer. But the studies that are ongoing, so like this one of trying to match neutrino emission on the galactic plane, which is a very crowded region for us, is one of the things that will help us to really identify the galactic sources of cosmic rays. We are also part of us involved in the southern version of Hawk, the SWGO. So hopefully by 2024, SWGO could be operating somewhere in Los Andes at close to 5,000 meters altitude. And what I really would like is to have Hawk observing at the same time as a SWGO, because we will be coincident in some parts of the sky. And other results that we are just about to release are AGN. So we're starting to see the first AGNs aside from Markarian 421 and 501 and also radio galaxies emitting.
Thank you very much. This means we will start looking for more excited results even for the future.
Sure, certainly, and I mean, we also have other topics that we can to present later on, like dark matter searches, for example.
Okay, Alberto, thank you very much for your very summary and explanation of all these results and of these limits Hawk is reaching.
My pleasure.
If you stop sharing, we will go to the next speaker, which is Arteaga Velázquez, talking about the potential of Matuzla for cosmic ray research. This is a very interesting detector for long-lived particles. If you may want to start. Thank you.
Thank you very much for the presentation and also for the invitation to talk with you about this Matuzla proposal in order to detect, to try to search for new physics and also to detect cosmic rays. So I'm basically going to give you a very brief summary about the physics potential of this proposal and also for the cosmic ray case. So let me talk to you a little bit about the motivation. Well, as you know, up to the moment, there are no signals of really up to physics beyond the standard model at the LHC. And that could be due to some limitations in the size, for example, of the LHC detectors. And that is maybe we are looking in the wrong place. How is that? Well, as you know, mainly the detectors at the LHC are looking from the case. That is the case of possible new particles that could be producing, could be decaying very close to the interaction point. But there could be also new neutral particles with very long lives, which we will call LPs, which may be escaping the detector without being observed, and they could be decay outside directly the interaction point. So these new particles could be not be observed at these LHC detectors and are very well theoretically motivated. They can appear, for example, in the context of different beyond standard model scenarios. And examples of this particle could be, for example, dark photons, actions, etc. So we need to complement the searches for beyond the standard model physics at the LHC. And one of these proposals is precisely Matuzla. The idea is to build a large area odoscope in order to look for the decay of these LPs in a very large volume of air. And the idea is to monitor this region by using tracking detectors. So the idea is to put one of these tracking systems at a given distance from one of the interaction points of in this case, the CMS, at 70 meters from this interaction point. That will be located on the surface, so you will have a lot of rock that will filter the signals that you want. And so you will control also the background for example, from QCD. That is planned to run in the next high luminosity LHC runs. So the idea is to put some restrictions in the mass of the MEVs at up to TeVs mass range, and also with the decay lengths from 0.1 up to 10 to the 7 meters. That is very close to the cosmological limits that we have. So the experimental design is basically a modular design of 100 meters by 100 meters, and that will be composed by several scintillator detectors, 9 meters by 10 meters each of these modules. So this is the corresponding configuration. You will have the trigger for this decays of these particles, which will be activated by 5 scintillator layers on the top. So then at ground level, you will have a double tracking layer to increase the performance. And here below, you have a veto for upward going particles. The technology that you want to use is basically some silicon photomultipliers coupled to scintillator bars with wavelength shifters. So the size of these bars will be 5 meters per 4 centimeters per 2 centimeters height. And the idea is to put the long direction in one layer and to rotate it in the next layer by 90 degrees. The spatial resolution is going to be around 1 centimeter and the time resolution about 1 nanoseconds. And this is the region that you are going to basically to try to study in order to try to monitor the decay of these possible new particles. So the Matula proposal will have then a lot of sources of backgrounds. For example, from neutrinos, which are coming from below, and also from muons, from the LAC interaction point, atmospheric neutrinos also, and also a lot of background from cosmic rays, so about 1.7 megahertz. This background from cosmic rays is one of the dominant one, together with the muons from the LAC interaction point. So, but by using this configuration that I have presented to you, you can basically reject a lot of background and mainly the dominant one, as is already studied by using this test stand that is presented in this slide. So this stand was put directly about the interaction point of the Atlas detector, and it took data during the 2018. Also during the Atlas runs, in order to try to look for in order to try to study the design of the Matula detector and try to measure also the dominant sources of background. That is the downward cosmic rays and also the upward standard model charged particles. These upward charged particles come directly from muons, from cosmic ray muons, which backscatter upwards, and also from muons directly coming from the interaction point at the Atlas. So these are the main sources of background in the detector. And this stand had 2 scintillator layers and 3 double RPC layers from the Argo experiment. So the time resolution was around 3 nanoseconds. And these are the results from this test stand, which prove the design of the Matula detector. So here you can see the downward cosmic ray simulations in yellow in comparison with the downward data from cosmic rays. You can see a very good agreement of this background. And this data is also backscatter upwards. And this upward scattering is observed here with blue. This is the simulation. And in orange, you see the corresponding simulation from the muons, which are coming from during the Atlas interaction points during the corresponding runs. And the data that is in comparison with the data, which is the dark data points, and you can see that there is a very good agreement. So there is no deviation between systematic and uncertainties. So that means that we can describe the background. The Monte Carlo simulations are in very good agreement with the corresponding data. And here below, you can see an example of upward going track that was reconstructed during this data taking. Now, Matuzla, it can also act as a cosmic ray detector. As I told you before, these cosmic rays are a source of background, but that is a very interesting source of information to study cosmic rays. Basically, we don't detect directly the cosmic rays. We detect indirectly the cosmic rays by using extensive air showers. These extensive air showers are produced by interaction of cosmic rays in the atmosphere. They produce a shower of particles at an altitude of around tens of kilometers above sea level, which arrive directly to the detector. That is what we observed, basically the shower. The shower has several components: an electromagnetic one, which is the dominant one, then that only one, which is less than 1%, and the second dominant component is the muonic one. So in order to make the studies of cosmic rays by using 2 extensive showers, you need to measure as many components as possible. Unfortunately, with the actual design of Matuzla, it's very problematic to do cosmic ray physics. Why? Because the detectors are saturated at one heat. So in order to improve the detector, we need to add an extra RPC layer. The idea is to add this layer at around 1 meter above the double middle scintillator layer, as you can see with this line over here. And the idea is to use an RPC and an analog mode in order to provide measurements of charged particles. That is electron plus muons. You can measure the linear, we expect a linear response that gives you then measurements of the densities up to 10 to the 4 charged particles per square, even per square meter. You can also measure the arrival times of the first particle per strip in the detector. And the idea is at the moment to use, for example, big path sizes, 2,500 or 2 meters by 2 meters. So this is one of the proposed configurations in order to enhance the detection of Methuselah for cosmic rays. So with that, you can provide information about the space-time structure of extensive air showers at a level that it was not possible to achieve in previous studies. So with simulations, at the moment, we were able to study the performance of Methuselah with these extra RPC layers to cosmic rays. So we have found that basically the Methuselah will be sensitive above 10 to the 5 GeVs approximately in energy, up to 10 to the 8 GeVs, as you can see from this plot on the left. So that basically you can study then cosmic rays in the energy range around the knee, which is basically associated with this structure that we can see around 10 to the 15 electron volts, which it seems to this studies produced by the end of galactic cosmic ray accelerators. And it's also directly located in the frontier between direct experiments and also indirect experiments. So basically we can expect around 10 to the 8 events above 10 to the 5 GeVs approximately per year in Methuselah. So that is very good in order to make composition studies, for example, and also to study the energy spectrum. There are several questions in cosmic rays that we still need to answer. For example, regarding the shapes of the energy spectrum for each of the individual elemental nuclei in the cosmic ray spectrum. And also to, for example, details about the relative abundances in the composition. This is very important because that can give you a lot of information about the acceleration mechanisms. It's also important to measure the anisotropies in the cosmic rays because that gives you information also about the spatial configuration of the sources and also the propagation of cosmic rays in our own galaxy. This is an example of the performance of Methuselah for cosmic rays producing vertical air showers. This is for a proton with almost 10 to the 16 electron volts and arriving almost from the vertical direction. So here is with the light blue, the position of the RPCs. The other are the scintillation planes. So basically you can see the very good answer for the arrival of these air showers. Here you can see the position of the shower core, and here is the corresponding performance for this example that I have shown you. On the left, you can see information about the density of particles. Here you can see very well the position of the core, which you can see.
We have 5 minutes.
Thank you very much. You can see the amplitude, which is proportional to the energy scale. You can see also the position of the core, and you can see the arrival directions of the particles with red electrons, with blue hadrons, and also with green the muons. So the inclination of this plane of the arrival times can give you information about the arrival direction of the particle. See, here is the performance regarding, for example, the pointing direction, which is at very high energies, close to 1 degree. And regarding to the core position, we can reconstruct it with a good spatial resolution of around 1 meter for vertical showers. And if you go to very inclined showers, you have that muons are more dominant because of the absorption of the electromagnetic component in the atmosphere. And that is very important because, for example, in experiment like OJ, there have been detected several important deviations between the muon data and also the predictions of different hadron interaction models for inclined air showers. So that is a very important point in order to look for in these very cosmic rays with inclined direction. So here is the performance of the detector for an inclined event from Monte Carlo with an arrival direction of 74 degrees and with an energy of around 10 to the 17 electron volts. So these events, as you can see over here, we can also detect the shower core, from, as you can see from the top plots, and these events are basically dominated by muons. That is what we want in order to try to study these possible differences with the Monte Carlo. This is the pointing resolution, which is below 1 degree, which is very good one in order to study these cosmic rays, and also the core resolution, which is very around 10 meters approximately, which is better than experiments like Cascade and also the Oyer Observatory. So this is a summary of the cosmic ray basically performance. Well, what we can do with expecting for Matula 100. So with this RPC, we have basically a full coverage. And as you can see from this table, there are no other running cosmic ray detector which has such capabilities. That will give you information about the temporal and spatial structure of air showers up to 80 degrees approximately, and that can give you new, very fresh data on muon showers in very inclined events around 10 to the 15 electron volts. The physics potential, well, we can study the cosmic ray spectrum and the composition to look for the anisotropies using this tracking detector configuration, study the structure of the air shower front, as cannot have been done before, to test hadronic direction models and to try to look for muon bundles. So this is the cosmic ray physics group. We are working in Mexico, for example, in Michoacán, also in Chiapas, in Puebla, in collaboration with the University of Washington, and also with Bolivia. We invite also people to participate if you want to join us. There are several documents which you can read, which are written in this link. And there is also a link, for example, for the Matuzla proposal, which is written here below. Now we are in the stage of writing a technical design report. As a summary, well, Matuzla can give you complementary information in the searches for new physics beyond the standard model at the LAC during the next high luminosity runs. And the detector is planned to be installed at the surface of the CMS interaction point. And also the Matuzla, the design actually is going to be composed of a tracking array of 9 planes of scintillator detectors, each of them by using a modular design. The detector can also work as a cosmic ray shower observatory, and its capabilities as a cosmic ray detector can be enhanced by using an extra RPC detector layer. With this extra layer, we can construct a different new brand instrument to study the spatial and temporal structure extensive showers, to test the prediction of hadronic interaction models, to study exotic, to look for exotic physics, for example, bundles in cosmic rays, and also to perform the research on some open issues of on the physics of PV cosmic rays and galactic cosmic rays. So thank you very much. If you have some questions, please.
Yes, thank you very much, Juan Carlos.
Yes,
we have a question from Cecilia. Cecilia, you want to make Cecilia Uribe? You may want to do the question yourself.
Okay, hello, very nice talk. Thank you very much. What kind of RPCs are you going to use for the site in the CMS site, and what kind of mix, the gas mixture you're going to use? Do you know those details?
What I know up to now is the design is based on one that was proved on the Argo detector that was used on the Argo detector based on a gas mixture. I don't remember the gas mixture, very interesting question. I have to add it in the next presentations. But actually what I can tell you is that it's going to be based on this Argo configuration.
Do you remember if it's bakelite or glass?
I'm not so sure really.
Okay, thank you.
Welcome.
Okay, excellent. Thank you very much. I think Argo was bakelite. It was from the Italians from Atlas, but thank you. We would like to know later. Okay, so thank you very much. Our next speaker, I think it will be, thank you very much, Jesus, for this nice presentation of the Matuzla and this experiment that is getting all these opportunities from the LAC to measure for these long-lived particles. So next we will have Mejia Camacho, and he will present initial development of a control system for the FDD detector in the ALICE experiment for the operation of LAC Run 3. Please, you may proceed.
Thank you. Can you hear me?
Yes, very well.
Okay, we'll share the screen.
You can start sharing.
Okay. Can you see my screen now?
No, no. Okay, it's coming. It's coming. It's taking a little bit of time. Okay, we only see it. Okay, you can start. Thank you.
Okay. Good morning. In this occasion, Juan Carlos Cabanillas and myself, we're going to talk mainly to the current status of the development of a control system for the fast interaction trigger diffractive detector in the ALICE experiment for operation on the Large Hadron Collider during round 3 next year. The topics that will be shown during the presentation are going to be diffractive event in ALICE, fast interaction trigger diffractive detector, hardware to be used with the fast interaction trigger detector control system, development methodology for the control system of the fast interaction trigger diffractive detector, and some conclusions. The main characteristics of the diffractive process is the presence of a significant gap in the distribution of speed of the particles produced during collision. That is, the absence of particles created in the collision whose direction is in a given interval. The study of diffractive events with boson production is important for the understanding of the proton composition, quarks and gluons inside the protons, of the exchange object called pomeron. In most high-energy experiments, the selection of diffractive events is made by using characteristics in different ways. The main characteristics of the diffractive process is the presence of significant gap in the distribution of speed of the particles produced during the collision. That is, the absence of particles created. The study of the diffractive production in Large Hadron Colliders at CERN is of great interest, both for theoretical and experimental reasons. The identification of diffractive events is not experimentally simple. At low energies, it is often possible to identify and measure the non-diffractive proton, but in Large Hadron Collider, this becomes a great challenge, so they must have alternative methods for high energies. The selection of diffractive events in ALICE is limited by range over which speed gaps could be detected. Therefore, it is possible to achieve better measurements by extending the range of directions in which the production of particles or absence of the particles can be detected. The study of diffractive events with ALICE experiments of the Large Hadron Collider in proton-proton, lead-lead, and proton-lead collisions could improve its efficiency with installation of the fast interaction trigger diffractive detector for round number 3 in 2021. The fast interaction trigger diffractive detector consists of two subdetectors called FDDA and FDDC. Each of them includes two detector layers, and each one of them consists of 4 scintillator modules arranged around the Large Hadron Collider beam pipe. The FDDA and FDDC designation refer to the installation position at both ends of ALICE cavern concerning the interaction point. The approximate distance between the interaction point and the FDDC and FDDA subdetectors is around 19 meters and 17 meters respectively. The fast interaction trigger diffractive detector is part of one of the 3 subdetectors that makes up ALICE fast interaction trigger project, together with the FT0 and FV0 subdetectors, which plan to start operating in 2021. The FDD detector will increase the time resolution compared with ALICE diffractive detector used in run number 2 between 2015 and 2019. And FDD will provide triggers at level of 0 for ALICE. The FDD detector will be installed at ends AOC, as you can see in the figure of the ALICE cavern for operation. The main device to satisfy the high voltage requirements for the FDD detector is a universal multi-channel power supply model SY4527 from the company Kind, which has 16 slots to place voltage boards and branch controllers, where the latter are used to control other remote generators and distributors. This source is going to be located in the counting room number 4 at the point number 2 of the Large Hadron Collider. The high voltage boards used inside the Universal Multi-Channel Power Supply System are from Kind as well. Model 7236, which have the ability to provide up to 12 high voltage channels. The output voltage of these boards can be set from 0 volts to 3.5 kilovolts with a maximum power of 4 watts per channel. 2 of these boards are going to be used for the FDD detector. 2 of these high voltage boards will be used to power the photomultipliers that collect the light coming from each modules of the FDD detector. The Tycho laser calibration system will allow the monitoring of the FDD detector to adjust parameters to guarantee the best performance. The electronics in the FDD for both subdetectors, FDD-A and FDD-C, are located in the VME crate, which use as a metal structure with the ability to interconnect electronic modules that are inserted into the slots of crate, as well as their power supplies. The main task of the ALICE experiment control system is to ensure the safe and correct operation of the experiment. In addition, provide remote control and monitoring of all experimental equipment so that the experiment can be operated from a single workplace. This place is known as the ALICE Room Control Center at the point 2 of the Large Hadron Collider, through a single set of operator panels or operated by remote users with access control permissions. The ALICE detector control system is based on a commercial supervisory control and data acquisition system named WinCC-OA, running on a large Windows computer clusters. In general, the detector control system is responsible for performing control, configuration, reading, and monitoring the hardware of devices. It performs hierarchical control of the subdetectors within ALICE experiment, as well as monitoring of external systems such as the Large Hadron Collider, electrical system, gas system, and some others. Now, Juan Carlos Cabanillas will continue talking for the next slides of the presentation. Please, Juan Carlos.
Okay, next one, please. Okay, can you hear me?
Yes, yes, you can proceed.
Okay, we explained the methodology. One of the main change in the run tree of the LHC is to process online the generated data from the ALICE experiment during collisions. This update the regulation of the online-offline infrastructure, also known as OSCORE, that will operate the ALICE experiment is currently being implemented in detail. So this design complies with these new standards. Next, please. We are using for this development a SCADA system named WinCC-OA and frameworks developed at CERN, such as Jacob, which are defined for ALICE and LHC experiments. Next, please. Okay, this is the software architecture currently proposed for the detector control system of the FDD detector, and it's compatible with the architecture required by the ALICE experiment. And the software architecture is a hierarchical tree structure representing the operation of the subsystem and hardware devices. Next, please. The hardware architecture currently defined for the FDD DCS is compatible with the architecture required by the ALICE experiment, and the FDD DCS will interact with different devices located in areas like counting room, cover, inside the magnet, with the objective of control, configuration, reading, and monitoring the hardware devices of such architecture. Next, please. In the control context, the finite state machine, also known as FSM's concept, is a generic and intuitive mechanism to model the functionality of the equipment, channel, or our entire subsystems. We can see an example to configuration of site A or site C of the different high voltage channels. Next. Next step is to modeling of the different nodes in the software architecture defined in the FSMs using using a unified modeling language diagrams. Next, please. The next step is to design the user interface for the different nodes in the software architecture, because it will allow to DCS shifter and feed on calls to interact with the subdetector, subsystem, devices, and equipment, keeping on the interface user-friendly. Next, please. Okay, in many applications, it's necessary to generate a chart of the trend of parameters such temperature, voltage, current, and other different of the different power supplies, ports, channels, and electronics parameters.
You have 5 minutes.
Next, please. Next, we will configure the alerts of critical parameters that have values outside of the nominal range or inspected values. To ensure the continuous operation of the FDD detector held for alarms, will specify it, which these alarm helms will consist of a set of procedures that the central DCS shifter in the ALICE experiment must follow to resolve the issue that triggered the alarm. Next, please.
That's the next one.
Okay. Next. Okay. And some parameters were defined which will be measured to know the FDD DCS performance in physics and different rooms, and its comparison with the other ALICE detector. Next, please. Next step is once DCS is working in the ALICE experiment, artificial intelligence algorithms are going to be developed with the object of solve limitations in the error recovery without human intervention in the operation of the control system. Next, please. Like conclusion, we can define like the software and hardware architecture already proposed will allow to release a fully operative FDD DCS to comply with the new O2 requirements of ALICE experiment. And other challenge is integrate the DCS in the continuous processing strategy defined for Run 3. Okay, that's all. That's all.
Thank you.
Thank you.
Excellent. Thank you. Very, very good presentation. I think you put very clear the full path or each step you have to do for installing and all this project for a detector. And it's very interesting how this fast trigger diffractive detector you will install and it will be used for the future in ALICE. So let me see if there is any question. Somebody is raising a hand for a question. I will let me check in the YouTube. So I think it was really very clear that how you express all the steps. It seems that you have a lot of way to go still and to learn, and probably in the process, and also all this WinCC software that CERN provided you must learn and know how to use. So my question will be related to how your specific contribution in the future, or your future contribution you are going to be doing, and if you're doing here or in Mexico or at CERN. Thank you. It was clear my question, so.
Yeah, about the can you hear me? About the contribution, is going to be right now, for example, there is no control system for the FDD detector since it's a new one, right? So the contribution right now is from the control system point of view is to make sure to have available the control system for the FDD detector. So this detector can measure and take some data during run tree, so he can be ready, right, for these steps. And the other contribution, perhaps in the 2022, will be to evaluate, right, artificial intelligence algorithms. So the system can recover for any, let's say, errors that right now the errors need human attention, right? So the idea is to avoid this, so can the computer or the system through the algorithm, so can fix the issue without human intervention.
And for example, in run 1 and run 2, where you set offline and online system. In this run 3, we allow the continuous data taking and a measure of online offline system in the on the O square. This new infrastructure will define it and design it for the DCS. It's new just for this development.
Excellent. This is very interesting. So we would like to hear from you in the future how this will at the end it will develop, and how is the contribution from you and your group working on this detector. Let me see if there is any other question. I think we are just 1 minute to finish. And okay, so if I don't see any more questions, I would really like to thank you, both of you, for your very nice and clear presentation, for this very good Alice's contribution. And we will have now a recess of, we will come back at 11:05. So it's 10:45. So please, we will resume our talk later at 11:05. So please take a break now. And thank you for everybody's participation in time. And so we wait for you in about 20 minutes. Thank you very much.
We shall be starting shortly.
So, hi Pablo, are you there?
Hi, yes, I am, Sergi.
So can I share my screen already?
Yes, please. Great.
So can
Yeah,
you see?
we see your slides and we see the pointer as well.
Okay, perfect.
Very good. Okay, so it's time to start back again. In this session, the first talk will be given by Dr. Sergi Gonzalez Solis, who will tell us about tau physics. He comes from Indiana University. Please, Sergi.
Yes, so first of all, I would like to thank the organizers for this kind invitation. I'm happy to participate in this online workshop. And yes, I'm going to talk about tau physics. And this is the outline of my presentation. I will start with an introduction, and then I will move to the technical part of describing hadronic form factors for tau decays. And then I will briefly move into the use of these hadronic form factors to constrain non-standard interactions, but only briefly because there will be a poster session by Javier Rendon where you can find further details. And finally, I will also describe, talk about some prospects for tau physics at Bell 2, but also briefly because next talk is there is a dedicated session for tau physics at Bell 2. So let's start with the introduction. So let me start by taking a look back in time and go to the discovery of the tau lepton, which was in 1975 at SLAC. Where
we are still seeing the first slide.
You are still on the first slide?
Yes.
Which first slide?
The presentation, the tau physics one, with your affiliation and name.
So you don't see, for example, now the outline?
No.
Oh my, okay. So I don't know why.
Maybe you can exit full screen and
maybe
work this way.
Try. So how about now?
Now we see the slide. Okay.
All right. So introduction. So I was here before. So yeah. So let me start by taking a look back in time and move and go to the discovery of the tau lepton, which was dated at 1975 at SLAC, where it was found some strange reactions from E plus E minus going to an electron and a muon plus some undetected particles, for which we had no conventional explanation at that time. And there were some suggestions that about the existence of new heavy leptons that can decay leptonically. And this precisely 2 years later, these new heavy leptons, which were named tau, were evidence at SLAC. And they became mainly leptonically to electrons and neutrinos, and also to muons and neutrinos as well. And these leptonic decays are mostly nowadays used to constrain to test the lepton universality. Using as an input the measure branching ratios, which adds up to 35% of the tau decay width. And as you can see, the universality is tested at a very high precision, in particular to 0.14% from only tau branching ratios. This lepton universality can also be tested using a semi-leptonic decays of tau lepton with one meson in the final state over the semi-leptonic decays of the meson, and altogether adds up to this averaging ratio of G tau over G mu, which is constrained at a very high accuracy. But the main difference of the tau lepton with respect to the other leptons, the electrons and the muons, is that it's very heavy, and it's the only lepton that is heavy enough that can decay into hadrons. This offers a very rich phenomenology and allow us to test QCD and electroweak interactions. And for this test, we need precise measurements. And also to have, it's important to have hadronic uncertainties well under control if we want to look for new physics. So we can divide these hadronic decays into two types, inclusive and exclusive. The inclusive decays are interesting because they allow us to extract some fundamental parameters of the standard model, like, for example, the strong coupling at the mass of the tau, or the mass of the strange quark, or also the BUS element of the Kabibo-Kobayashi-Maskawa matrix. But in this talk, I will mostly focus on the exclusive decays, which are useful to study the hadronization of QCD currents, to describe hadronic form factors, and to extract the resonance parameters of the intermediate resonances that are produced in the decay. So these hadronic tau decays can be classified in terms of the number of hadrons in the final state. For example, if we have only one meson, the only relevant quantity that we need, hadronic quantity, is the corresponding meson decay constant. And these are very well known from the lattice. Then we have also two meson tau decays for which we have a good control over them, as we will see in a moment. And then we have higher multiplicity tau decays for which we have a reasonable or poor control over. Here I show in particular the amplitude for a two meson tau decay, which is given by an electroweak part times an hadronic matrix element. And this hadronic matrix element is given in turn in terms of a vector and a scalar form factor, which are the quantities we need to have good control over. In particular, the pion final state, it's very interesting because it's very rich phenomenologically, and allow us to get some insights on the properties of the rho meson family. Also, the K-short pi minus decay channel is very interesting for several reasons. For example, for the extraction of the BUS CKM element, and also to study the properties of the K-star family of resonances. And finally, there are the isospin violating pi eta decay channels are also very challenging for Bell 2, and we have to provide some theoretical predictions. So let's move to the technical side and describe hadronic form factors from chiral perturbation theory and supplemented with dispersion relations. So the pion vector form factor is this object that you can see here, is the black blob, which describes the physics within this black blob. And this is a very important object because it enters the description of many physical processes, like, for example, the hadronic contribution to the G-T of the muon, as we have seen in the first talk today. So from the experimental side, we have a high statistics measurement from Bell from 2008, which is sensitive not only to the rho peak, but also to the destructive interference between the rho prime and rho prime prime vector meson resonances. And one of our goals in the following will be to improve the description of the second half of the spectrum, where these higher resonances lies. So the first question we have to ask ourselves is how to determine this vector form factor experimentally. So, well, you can extract it from tau decays, or also from the E plus E minus going to 2 pion reaction. And the only difference between them is that one is driven by the charged rho, and the other one it's dominated by the neutral rho. And so the effects of the rho omega mixing should be taken into account. And also the difference between them is that there are some For example, taking the ratio between them, you can get some insights about the strength of isospin violation. And if you want to know more on that, there will be a dedicated poster session by Alejandro Miranda about this issue. So what do we know on the theory side? We know it's low energy behavior, which is given by chiral perturbation theory. We also know it's high energy behavior, which is given by perturbative QCD that tell us that the form factor should behave as 1 over S. And then for the intermediate energy region, we need some models, and we need these models to be as model independent as possible. So let's just start from the beginning, and let's describe the pion vector form factor with chiral perturbation theory and next to leading order. We have these contributions, the contact term, the loop contributions, and the contact term and next to leading order, which give us this expression here. Then if you plot this expression, you see that it fails dramatically to describe data, but this is not a surprise because, as you can imagine, a chiral perturbation theory is based on a polynomial expansion, and a polynomial expansion cannot describe a resonance pole. So in order to improve on that, one need to rely on resonance chiral theory, which includes the resonances at explicit degrees of freedom, and then comparing the expression with chiral perturbation theory with the expansion of this new expression, including resonances, one can get estimates of the chiral low energy constants. Then combining both expressions, chiral perturbation theory and the resonance chiral prediction, you end up with this expression here. But this expression here is still has some limitations because one need to, it cannot describe the rho meson peak because we need to include the rho meson width. And also, we will also like to resum the whole set of pion-pion unitarity corrections, not only at first order. So in order to improve on that, we will use the dispersive formalism, which tell us that the 2 pion contribution to the discontinuity of the form factor is given in terms of the pion vector form factor itself times the pion-pion p-wave scattering amplitude, which in turn can be given in terms of the corresponding pi-pi phase shift. And then if you plug this discontinuity into a Cauchy dispersion relation, you end up with the very well-known omnes equation, which is given by this omega expression here. So this kind of equation allows us to resume the whole set of pion-pion unitarity corrections to all orders. So, but we still need to, we still have a polynomial ambiguity, and we need to get a model for the phase. In order to get a model for the phase, initially we can rely on chiral perturbation theory at leading order, which is given by this so-called Weinberg amplitude that you can project in partial waves, and then you can extract the corresponding phase and plug it into a dispersion relation. In doing so, you end up with this expression here, and you generate the whole set of pion-pion loop corrections. And as for the polynomial, we fix it to the chiral amplitude with resonances and resum the rho meson width into the resonance propagator. And in doing so, we only have one free parameter, which is the rho meson mass input that we feed to data. And you can see here that the fit describes very well the elastic region where the rho peak dominates, but fails to describe the second half of the spectrum where higher resonance excitations show up. These higher resonance excitations can be included in a similar fashion, given by this expression here, where these extra parameters denoted by the gamma and delta and these phases takes into account the contribution of the second and third resonances with respect to the first one, to the rho. So then we perform a fit including all these contributions, and this is the result of our fit as obtained with the exponential representation. And as you can see, it's very satisfactory. And these are you can find here the corresponding fig parameters. But there are still some drawbacks associated to this representation, which is that the constraints from analyticity and unitarity and of chiral symmetry to some extent are not fully respected. And in order to improve on that, we will make use of dispersion relations with subtractions, and which is given by this expression here. And as it is of capital importance, I will spend some time explaining it. Alpha 1 and alpha 2 are some subtraction constants that have to do with the low energy behavior of the form factor, for which we have some predictions from chiral perturbation theory given by this expression here, but they can also be predicted by a sum rule, which is totally given in terms of the phase shift. So then we have this integral cutoff, which is used to test the stability of our results and also to allow us to include a kind of theoretical systematic uncertainty. So all what we need next is to get a model for the phase. So for the phase from the 2 pion threshold to 1 GeV, so within the elastic region, we will make use of the pion-pion phase shift, which is well known from the solution of Roy equations and describes data very well, as you can see in this plot. Then from the 1 GeV to the mass of the tau, we will make use of this phenomenological phase given by this expression here, which is extracted from the exponential representation that we have presented before with 3 resonances. And then from the mass of the tau on, we will send smoothly the phase 2 pi in order to fulfill the high energy behavior given by perturbative QCD. So in doing so, we get some, we perform some fits, varying the integral cutoff, and these are the results. These are just numbers, but this is better illustrated graphically through this plot, where you can find the phase shift of the pion vector form factor. And as I said, from threshold to 1 GeV, it's fully determined by the pion-pion phase shift. And then this is our models depending of the variation of the integral cutoff. And then we send smoothly the phase 2 pi. And as this object is very used in phenomenology, if you are interested, you can find the results in tables as a supplementary material in our paper. This is for the phase, and this is for the absolute value square of the form factor. And as you can see, we are accommodating the data, experimental data from Bell measurements, very, very satisfactory. So these are the central results of our fits, which are given by their central values plus statistical uncertainty. And also we have taking into account as a novelty in our work, different variations of theoretical representations that allow us to include for the first time, some systematic theoretical errors, which are given by the second error. And we have found that they are indeed dominating the errors of the higher resonance excitations. These are fit parameters, and these are the physical pole mass and width of the resonances, which are the universal quantities you have to look at and to compare with different models. So we here in this table, we collect our results, compare with other results in the literature, and as we made some emphasis in our works, that in order to compare on the same footing with different parameterizations, you should look at the pole parameters. As for the low energy observables, that is the subtraction constants, these are the results of our work for the pion radius, and as you can see, our result is pretty precise with respect to the other determinations in the literature. And we have also determined the curvature of the form factor, and it's also quite precise. And not only that, we also compare the result of our fitted subtraction constants with the results given by the sum rule. And we have found that the model we are using as an input for the phase saturates very well the dispersion relation. So this was for the pion vector form factor. Now we move to the kaon vector form factor, whose invariant mass distribution for the tau decay to the kaons is given by this expression here. And we can perform a similar bottom-up description, starting with chiral perturbation theory, and extract the corresponding isospin 1 component of the decay-on vector form factor, which reads exactly the same as the pion vector form factor at next to leading order. So we make an assumption and consider that both are also the same at higher energies. But of course, now we have to let the extra parameters to float, because there is no a priori no reason for being the same, since they can couple differently. So we perform the same game. We extract the corresponding phase shift with this expression, and we plug it into a dispersion relation. And these are the results of our fits. And as you can see, they are accommodating the data pretty well. But still, the data is not very precise. And this has a drawback, because then we cannot extract the corresponding resonance parameters from this decay channel as precise as from the KM ones, as you can see on the plots of the rights for the mass and the width of the rho prime. So then obviously we can also perform a combined analysis to both the deep ion and the decay channels, but still we have a limitation, because to improve on that, because the decay channel is still not very as precisely determined as the pion vector form factor. So now let's move on to a classic decay, which is the tau2k short pi minus. This is the Bell measurement from 2007, and as you can see, it's clearly determined by the K star 892 peak, which is neatly seen here, and which is very well determined experimentally with small error bars. But the second half of the spectrum, where the higher excitations, like for example the K star prime, K star 1410, show up, it's not as precisely determined. So in order to improve on that, we consider to perform a combined fit and add the tau2k minus zeta decay channel to constrain the corresponding resonance parameters. So we can perform the same game as previously. We can compute this starting with chiral perturbation theory supplemented by resonances, and extract the phase from these Bray-Wigner-like expressions, and plug the corresponding phase into a dispersion relation, and feed the subtraction constants, move the integral cutoff to check the stability of the fits, and so on and so forth. So we have performed this, and this is the graphical account of our results. The red points corresponds to the K short pi minus decay channel, while the green ones corresponds to the K minus eta decay channel. And as you can see, the K short pi minus channel is vastly dominated by the vector form factor. Only the scalar contributions only are relevant at very low energies to describe these very first points close to threshold, but then it's neatly and visibly dominated by the K star 892, which we describe perfectly. And then we have this shoulder corresponding to the K star 1410 resonance. On the contrary, given the threshold of the K minus eta decay channel, this one is dominated by the K star prime resonance, and also the scalar contributions are pretty insignificant. So these are just numbers for our fits. This is our reference fit, but we have also considered other fits, considering the different weight of resonances to be the same or not to be the same. We also have considered fits fixing the subtraction constants to be the same, or letting them float and be different in both decay channels. And also we have performed fits by taking into account variations of the integral cutoff, and then these allow us to extract the resonance parameters of the K star 892 and K star 1410, and as a result of our combined fit, we have no gain in including the K minus eta decay channel to improve on the determination of the K star 892 resonance as expected, because is dominated by the K-star prime, but we have been able to extract the mass and width of the K-star prime with improved precision, as you can see here in these plots. This is our determination with respect to the individual determination from the individual channels that has been performed before. So then we have also noticed that there might be some issues on the subtraction constant that might point out to potential isospin violations, because we have found that the subtraction constants of both decay channels slightly differ, in particular for the slope. And in order to improve on that, it could be very interesting to get measured the broader reaction K minus pi 0 decay channel, which was indeed measured by Babar, but this data is not publicly available, and moreover the data has not been unfolded. So hopefully maybe at Bell 2 they can get this channel measured again. So now we are going to use briefly all this machinery to constrain the standard model effective field theory Lagrangian with dimension 6 operators. So in the tau sector, the standard model versus non-standard model, there are not a lot of tensions. There is only some small tensions seen in the lepton flavor universality violation of around 2.5 sigma for this ratio of these couplings involving taus in the final state of the decay of the W boson. There is also a long-standing tension of the CP asymmetry of tau to K short pi minus, which is measured to be minus 3.6 10 to the minus 3 experimentally, compared to the standard model prediction, which is in absolute value the same, but with the opposite sign, 3.6. But apart from that, everything else looks like very standard model-like. Nonetheless, we are still, as we have all this machinery for this hadronic, for the description of these hadronic form factors, we are wondering why not to constrain the standard model effective Lagrangian with dimension 6 operators and use these form factors to get some bounds on the corresponding low energy constants. So we have performed a global fit, including all these sets of decays, that strangeness conserving decays with one meson in the final state and also with two mesons in the final state, where the form factors come up into play. And we have used, of course, the corresponding decay constants from the lattice to avoid get contaminated from new physics effects from the measurements. And this is just some numbers of what we get for these coefficients. And of course, I will not say more in this respect, because we will have a more dedicated poster session by Javier Rendon today. And just to mention that the results of our fits start being compatible with other extractions in the literature from kaon decays and also from inclusive tau decays. So the better the data will be in Bell 2, the better these coefficients will be constrained. So now let me briefly also discuss some prospects for tau physics at Bell 2. At Bell 2, as you can see here, the number of tau pairs will increase significantly with respect to Bell 1 by 3 orders of magnitude, and also 3 orders of magnitude more than Babar, and much more than Lep and Cleo. So there will be a huge amount of data to be delivered in the following years. This makes the tau lepton physics very, very interesting and an active field for searching, for example, for lepton flavor violation, for looking for CP violation, and also to to discover the second-class currents and some other interesting things like electric dipole moments and so on. So if you're interested on what's going on at Bell 2, you can check the white paper given in this reference here, archive the reference, or you can also stay tuned and wait for the next talk by Marcela, which will be talking about tau physics at Bell 2. So just to get some insights, these searches for charged electron flavor violation can be obtained from purely radiative decays, from leptonic decays with 3 lepton different than taus in the final state, or with 1 lepton in the final state by 1 meson that can be a pseudo-scalar, a scalar, or a vector.
10 minutes.
Okay, and as you can see in this plot here, the expected bounds from Bell 2 are pushed 1 or 2 orders of magnitude with respect to the predecessor B factories. So it's gonna be a very, very active and interesting field. So any observation of charged electron flavor violation would be a clear signal of new physics. So then we have also this CP asymmetry that we already mentioned briefly, which is the standard model prediction is given by this expression here, with this epsilon is the mixing of the K0 and K0 bar, the mixing of K0 and K0 bar, and therefore the prediction it's positive, and it's given by this number here, and it's experimentally measured to be minus 3.6. So there is a discrepancy of around 3 sigmas. This has been tried to be explained, including new physics, like for example through charge Higgs or through leptoquarks or W left, W right mixing, also including some tensor interactions, but it's very difficult to explain this tension. So it's clearly an improved measurement of this asymmetry. It should be a priority for Bell 2. Then we have the issue of second-class currents, which are the hadronic currents can be classified according to the spin and parity and G parity, and the second-class current ones belongs to this class of quantum numbers, and they have been not observed yet in nature. So in the standard model, there are some predictions for these tau to pi eta decay channels that proceed entirely by second-class currents. So in the isospin limit of the standard model, they are 0. So this means that they have tiny branching ratios of the order of 10 to the minus 5. There have been some searches for these processes in the last B factories, Bell and Babar, and we have these are the present limits, the upper bounds, and the standard model respects this bound so far. And therefore, the observation of these second-class currents in nature, it should be also a priority at Bell 2, and a clear signal would suggest definitely new physics. So let me go to the outlook. As I tried to convince you, hadronic tau physics is a privileged tool for the investigation of QCD and electroweak interactions, but not only. It's also interesting. Provides an interesting tool as a laboratory of new physics. And there is an important experimental activity at Bell 2, Babar, LHCb, and BESS 3. And so there is a lot of interesting physics to be done in the tau sector in the coming years. So thank you so much, and I'm happy to answer and interact with you all your questions.
Thank you, Sergi, for being so well in time. We have plenty of time for questions, so
Perfect.
I invite you to start with them, Salvador.
I have many of extra slides, so if you want more details.
It will be nice. I don't see questions now, or let me check the YouTube. No, maybe people was still waiting for you to continue. No question up to now. Oh yes, Gabriel Lopez, please, if you can proceed, Gabriel.
Yes, thank you. I have a question related to the program to get new physics from tau decays. Sorry?
Albel 2?
No. In general, with the existing data. In the first part of your talk, you described the hadronic physics or the hadronic tau decays, and you have shown that the data is able to provide information on hadronic resonances, the mass of the rho and the mass of the K star and so on. But if you want to explore new physics, you have to redo completely the fit to the data. I think there should be correlations between new physics effects and resonances parameters.
That's correct. That's correct. Let me try to answer your question by going here. So, for example, here we try to constrain the dimension 6 Lagrangian of the standard model effective field theory, using as an input our fits using as an input our hadronic form factor extracted from fits to experimental data, right? So these fits, these hadronic form factors can be already absorbing, can be contaminated from potential new physics effects that are in the data, right?
Mm-hmm.
So, and then we use them to constrain these low energy constants. We have tried to perform also a fit, including all together, but at the present moment the statistic is not as precise to get good bounds for these coefficients. What I want to say is that of course we need to improve both on the experimental measurements and on the theoretical predictions. If you are able to describe these hadronic form factors perfectly in the standard model, so it could be very useful to use them as an input for searches of new physics, because there will be no contaminated. This is what we are trying to do, using this dispersive formalism and using as an input the least possible things. I don't know if this answered a bit your question, because of course these new physics effects, if they are in the data and we are fitting data, we can absorb them into our theoretical parametrizations.
That's right.
So if you have a way to describe these hadronic inputs from first principles and with no contamination, that would be the best way scenario to constrain new physics.
Yes. So, but the best first principle results are just chiral perturbation theory or resonance chiral theory. That's right.
Exactly. Well, yeah, it started with Gasser and Leubiri in the mid 80s with chiral perturbation theory and including resonances. Then you can also try to make these predictions less model dependent by supplementing them with expression relations and play a little bit with all that, which is what we try to do. Also, we try to, for example, at least within the elastic region, we are using for the pion vector form factor the pion phase shift, which is well known from chiral perturbation theory, right? So we believe that if we move in this direction and get these inputs from the standard model as less model independent as possible, it would be very useful. But this should go together with having better quality data and see what can we get. Yeah, for example, my suggestion, if you want to improve on these vector form factors, would be to do an analysis, a detailed analysis of the K-pi phase shift, and then do a couplet channels analysis dispersively of pi and KK, for example, and all these things. But this is very elaborated.
I have another question. If
yeah,
possible.
Go ahead.
Yes.
Yeah, okay. Maybe just to finish, just to mention, because let me mention that it's cleaner. It's cleaner if we use, instead of 2 mesons in the final state for looking at new physics, you use this 1 meson final state, because you only have only have the pion decaying constant as an input, and this is well constrained by the lattice. So in this case, if we believe the lattice QC is correct, everything else is it's calculated. So it's cleaner, no?
Yes.
Yeah.
Okay. And my second question is related to the isospin breaking. In your talk, you looked at the tau decays into pi.
Yes.
And you also have the neutral channel in E plus E minus.
Correct.
In both cases, you have small effects of radiative corrections that are available in the literature. So if you do a similar analysis in E plus E minus, you can get also the mass of the rho as the only free parameter, I guess. And in that case, how it looks isospin breaking in the mass and in the width of the rho?
This is an interesting question that I thought sometimes. Let me answer it using these 2 plots. On the plot of the left, it's the vector form factor from tau decays, and on the right from E plus E minus. So far, we only fit the one from tau decays, and it could be interesting to use our description and just to plot it against the E plus E minus ones and see how it goes. Because differences would be, as you said, given by isospin violation contributions among other potential things. Because here you also have the contribution of a rho prime prime prime, because here you are constrained by the phase space to the mass of the tau, while here you have larger energy to explore. So it could be interesting to perform a combined analysis, including isospin violating terms, to get the strength of isospin violation. This could be interesting, and also this you can also perform individual fits to this pion vector form factor and extract the same parameters, and see how this isospin violation affects to the pole position. This can be done.
Okay. Would be interesting to do it.
There is one more question from Wolby, sorry.
Yes, it is a simple follow-up question to Gabriel. You consider these dimension 6 operators, which could be there and could be beyond the standard model, but as a very high energy effect. But now you're discussing then low energy constants, which come in the chiral perturbation theory as a low energy expansion. So it is not even obvious to me if they would actually be affected by possible dimension 6 operators.
So you mentioned that the low energy constant that I'm using as an input might be contaminated from higher dimension operators?
Rather the other way around. Let's say we have a tiny coefficient for such a...
Well, this goes very similar to what of course.
Energy constant, or?
Yes, of course. For example, in KPT, if you can express the low energy constants in terms of the corresponding resonance contributions. For example, you can see here, this as an example, the L9 coefficient of the chiral Lagrangian, and next to the order is given in terms of the rho. But if you include higher resonance excitation like rho prime, and so on, they also contribute in here. And same would happen. So then you can also include very heavy vector contributions here, because if you feed them from data, they will absorb this contribution. So if you fix these coefficients from data, of course, data includes everything, no? So you cannot disentangle the contribution of each one. So that's why, for example, if you give me these coefficients from as model independent as possible, so this will reduce the pollution for searches for new physics. But yeah, definitely here you can make a prediction including as many resonance you want. And then of course if you use this as an input for the dimension 6 of Lagrangian, this introduce a source of uncertainty.
Okay, thank you.
Yeah, I'm sorry we are over. So thanks a lot again,
Yeah.
Sergi and everyone.
Thank you for all you.
And we move to the next talk that will be given by Marcela Garcia. Please unmute your microphone if you have not done so already. And please start sharing your screen at your convenience.
Okay, give me 1 second, please.
Sure.
So you can see, I don't know if you can see my presentation.
Please don't put it full screen because it can give problems. This way is right.
Okay. So, okay, so I'm going to start. So hello, everyone. In this talk, I will give you an overview of the current ongoing studies of tau physics at Bell 2 and the more advanced ones. So first of all, let me talk about the Bell 2 experiment. The Bell 2 experiment, as you may know, is a major upgrade of Bell. Bell 2 is the name of the detector, and its accelerator, SuperKP, is designed to increase the instantaneous luminosity 40 times larger than the one that we have in Bell, and also larger than other previous experiments. The good news here is that the last June, SuperKP reached an instantaneous luminosity of 2.22 times 10 to the 34. And with this, we're climbing the world's highest luminosity record from LHC. So Bell 2 is a super factory experiment. And it's designed to find new physics beyond the standard model. As was mentioned before, there is a lot of physics prospects and had been documented here in the Bell 2 physics book. So please take a look to this. And moreover, there are more than 1,000 active members from more than 100 institutes and 26 countries in the Bell 2 collaboration. And among them is Investap, Mexico. So in this slide and then next, I will give you more details about SuperKP and the Bell 2 detector. So SuperKP is an electron-positron asymmetric beam collider in which the electrons and positrons with these energies collide here at the center of the Bell 2 experiment in the interaction point at the center of mass energy of the Upsilon 4s mass. Here, mainly beam mesons are produced. That's why this is a B factory. And one of the new features of this collider is the nanobeam scheme. That the basic idea of this is to squeeze the beam. And also we increase the beam current. So once these parameters reach these values, SuperKP will achieve its design instantaneous luminosity, which is 8 times 10 to the 35. Now, Bell 2 is the tool for the upcoming discoveries. So I will explain the main components of this detector, starting from the inside to the outside. So first we have a tracking system that is composed of the vertex detector and central read chamber, followed by a particle identification system comprised of two Cherenkov detectors. Next, we have an electrocalorimeter, and in the outer region, the K-long and muon detector. So here, all the components are either new or considerably upgraded. So some examples of these upgrades also are the trigger and DAQ system due to the high event rates and background rates, and also the software of Bell 2. And just to finish this first section, I will give you some remarks. So the first physics room was at the end of 2018. And since then, everything has continued as planned, even during the COVID-19 emergency. The total integrated luminosity so far is 74.1 inverse femtobar. And the current situation is that we are in summer shutdown since July 1st. So next slide. From now on, I will focus in the tau physics. So why do we study tau physics at Bell 2? Well, because it's fun and because Bell 2 produces as many tau leptons as V mesons. So you can see here the cross section. That's why we consider tau as a Bell as a tau factory. Thus, the Bell 2 experiment will offer fantastic possibilities to study tau physics with high precision. And as you may know, the factories have provided many interesting results of tau leptons in the previous years. And Bell 2 will update and improve these results. Moreover, studies of tau leptons are extremely convenient because we can search on new physics, determine standard model basic parameters, do precise tests of electroweak interactions. And for example, you can see here on the bottom that the upper limits for the lepton flavor violating the tau decay channels at the 50 inverse femtobar. The prediction of Bell 2 is the improvement of 2 orders of magnitude. In the next slide, I will explain the ongoing studies of the tau physics group at Bell 2. So some examples of these are the mass measurement, is the lepton flavor violating tau decay channels. And also, as was mentioned before, we can measure a CP violation in this channel with K-short pion neutrino, and also looking for new physics in eta pi neutrino. So as you can see here, Simvestab is actively involved in most of these analysis. So I will explain with more details this analysis in the following slides. But first, I just wanted to mention that we have been doing performance studies using tau physics. So for example, studies with the trigger efficiencies at Bell 2 using 3-1-3 prong topology or 1-1 prong topology, so 4 or 2 tracks in the event. For this, the triggers related to the electrocalorimeter are the more relevant, and also tracking studies. So here we can calculate a quantity related with the reconstruction efficiency for the 1-3 prong topology using the Tag-Brook method, and calculating this quantity with the number of tracks that we are reconstructing. Also calculate this fake rake, just allowing another charge tracks here and calculating this ratio. So both of these results will be presented in iChep this summer. Now going back to the mass measurement, this is a important result because it's telling us that we are reconstructing correctly taus at Bell 2, and also is related with lepton universality measurements. So the measurement here is performed in the decay mode of 3 pions and neutrino, and using the pseudomass technique developed by the Argus collaboration. You can see here the quantity that is related with the mass of the 3 pions, the momentum of the energy of one of the beams. So here is the distribution of this quantity, and performing a fit here, we can estimate the tau lepton mass. Here you can see some results from Bell. for example, but here this result was dominated by the systematics. Also, the best three collaboration performed this measurement using another method, and this is the result. And for Bell 2, we performed a preliminary study with the early data, and this was the result, but even we are in agreement with a previous experiment, we didn't consider the uncertainties here. But the update of this measurement is complete and is under review. So I just wanted to give you some details and some spoilers. So this is a blind analysis. This was made using a blind analysis method, performing in 8.76 inverse femtobar, that is 30 times more statistics than the previous Bell 2 preliminary result. And also here, detailed studies of systematic uncertainties have been performed and are expected to be lower than in the previous measurement by Bell. So I put here a list of these systematic uncertainties. And the spoiler here is that these four, the last four are negligible. Also, for Bell 2, the uncertainty of the bin energy is less than in Bell, that it was the dominant in Bell. And we are, for the moment, these two, blue and pink, are the dominant, but we are going to recalculate the uncertainty due to the momentum shift of the magnetic field with data after the unblinding of this measurement. So the unblinding process is ongoing, and the result with this integrated luminosity with the data will be presented also in ICHEP this summer. Now, moving to the lepton flavor violating tau decay channels, I'm going to start with this tau to lepton alpha, where alpha is assumed to be an invisible, long-lived, massive, beyond the standard model boson. So, where this study were done previous by the Mark III and the Argus collaboration with this integrated luminosity. And the basic idea here is given by Argus is to fit the distribution of the momentum of the lepton in a pseudo rest frame. So you perform a Lorentz boost to this rest frame where you can, this two body decay is going to shape as a peak depending of the mass of the alpha particle. And here we can set an upper limit on this right chain ratio. For example, here you can see the results of Argus. Now, in Bell 2, what we do is to reconstruct 4 tracks in the final state. So one is the lepton. For the moment, we are analyzing the electron. And in the other side, 3 pions. So here we split the event using this thrust vector that is the vector that maximize this quantity that we call thrust. So we have our signal side and our tag side. Also, we require basic codes of quality of these tracks, and we require just 4 tracks and a common vertex here for the 3 pions on the tag side. So with this reconstruction, also we can reconstruct the standard model channel, and we can perform a background suppression using this standard model channel just to avoid to choose a specific mass for the alpha particle. We are using a figure of merit to optimize some codes in order to reduce the background, for example, using these 3 variables. One is this thrust value, other is all the visible energy on the event, another is the invariant mass of these 3 pions. So at the end, we get this 30% of efficiency and this 92% of purity. And then after the suppression of the background after the suppression of the background, we can perform this Lorentz boost to this pseudo rest frame. So the idea here is to boost the momentum of the lepton in the tau rest frame. But because in the tag side we are losing the neutrino, we don't know the direction of this tau. So we need to make some assumptions about the direction of this tau. So we can approximate the direction of this tau using the direction of the 3 pions. And also we can say that the energy of the tau is approximately the energy of one of the pins divided by 2. Another method is to use the direction of this truss vector that I mentioned before, because we know that this truss is going to point in the direction of the signal. So you can see here on the right, the distribution of the momentum of the lepton for the moment the electron. Here is, you can see the distribution of the 3 body decay standard model and the new physics for when we are using the direction of the 3 pions, and on the bottom when we are using the direction of this truss vector. And in these variables, we can start to calculate the upper limit on the branching ratios. On this ratio, on the branching ratios, as I mentioned, using the standard model channel as a normalization channel. This is going to be our point of interest, and this is our data model. So we are going to use a confidence level method that is a modified frequencies approach, and using the asymptotic approximation because it's faster. And at the 90% of confidence level, you can see here on the left the results. This is the previous result given by Argus. This Argus like is when we are using the direction of the 3 pions, and this truss is using the direction of truss. So here in this plot, you can see that we expect to have an improvement, but I need to say that this is a work in progress, and we are not considering the uncertainties here. But more details will be presented also in iShape. Now moving to the golden channels, we have lepton plus gamma that is very suppressed within the standard model, as we know. These are the previous results given by Bell and Babar. And we have the predictions of the beyond standard model theories. So Bell 2 can test these predictions. So in Bell 2, we reconstruct this channel using 2 charge tracks, one prong topology on the signal and tag side. Then we apply the background suppression as in previous studies. And in order to evaluate the signal yield, we use these 2 variables, the invariant mass and the delta E of the system. And additionally, we can perform a rotation here in order to have a good separation of the background and the signal. So at the end, we can select a region without any background events, so a region free of background. And this can be seen in the improvement of the upper limit of the branching ratio. So for example, here this is the prediction for 1 inverse attobar. And here in SimVestat, we perform a cross-check of this result that can be seen in the Bell 2 Physics book. And currently, we are updating this analysis with more realistic background, improving the tools of the simulation and reconstruction. Okay, and also performing trigger studies. The new estimations will be released soon. Now, other golden channel is the 3 leptons. Here, the idea is similar to the lepton plus gamma. Also, for the signal yield, we are doing this rotation and we are selecting our signal region. Just the difference is that here we are reconstructing, for example, the 3 muons. And you can see here a preliminary result for Bell 2 compared with this from Babar at this integrated luminosity. And here in SimVestat, we are also performing studies with 3 leptons, considering all the allowed combination between the electron and muons. For example, 2 muons and electron, 2 electrons and muons. Okay, so now just a summary. The Bell 2 experiment is suitable to study tau physics. A brief overview of tau physics at Bell 2 was presented here, focusing on the studies where SimVestat group is involved and the results that will be presented in iChat. Different studies can be performed with the data accumulated so far. So, for example, improvements on standard model basic parameters, searches of new physics on leptofluoride latent channels, and we are going to continue doing performance studies. And the upcoming data taken for the next year will be used to improve tau physics measurement and also search for new physics scenarios. So that's all. Thank you for listening.
Thank you very much, Marcela. Questions, Salvador?
No, I don't see any raise hands or question in the chat. Let me check YouTube. We have now 30 people in the YouTube. Okay, no questions up to now.
So let me just point out that you are doing great. And if data lasts a bit more than expected, then you explore other methods as you are doing with the invisible searches. And I think that's quite valuable. Taking into account the current data, when do you think that you can get to a publication in this particular decay mode?
Oh, well, it's just question to continue working very hard. So I hope very soon in the next months, we can have something to share.
Mm-hmm. Okay, we'll still stay tuned. Thank you very much again, Marcela. And we move to the next speaker, Daniel Enrique Ricalde Herman, who will tell us about background noise characterization and simulation on the LabM. Please start sharing your screen and unmute your microphone.
Yes, I will start.
Thank you.
Okay, hello, my name is Daniel Ricalde, and I will talk about the background noise characterization and simulation on the LABM. In this presentation, I will talk about these topics. First, I will give just a brief introduction to the issue at hand, and a really small introduction to the Belt experiment, the beam stratum radiation, the synchrotron radiation. Then I will talk about the experimental setup of the LABM, the simulation, and the data analysis. Finally, I will just give some conclusions and the work perspective. One of the most important things about for a particle accelerator is to achieve the higher number of collisions per event possible. This is measured with the luminosity. In Belt 2, the goal is to obtain 8 times 10 to the 35 of luminosity. But right now, the record is set at 2.4 times 10 to the 34. So this means that there is still a lot of work to do. One way to increase the luminosity is to have a good beam alignment for the collisions. For this, there are different beam monitors that measure the beam parameters along the accelerator. But still, we cannot get these beam parameters at the interaction region. For this reason, it's difficult to apply the corrections necessary to get a better beam alignment. Therefore, it's hard to obtain a higher luminosity by aligning the beams. This is the goal of the large angle beam stratum monitor, to obtain the beam parameters at the interaction region using the radiation emitted during the collisions. The Belt 2 experiments uses the B pair production to search for new physics. The LABM is part of the Belt 2 experiment, which is at the Super Cake B, a particle accelerator that collides 7 GeV electrons and 4 GeV positrons. Here it's a scheme of the Super Cake B. You can see here that there is the Belt 2 experiment. The LABM will be located in this part and also in this part. So one of the emitted radiations during the collision is the beam stratum radiation. This is generated when a charged relativistic particle is deviated by the interaction with the electromagnetic fields generated by another particle. So to explain this better, we have this small image. This one will be an electron. This is a positron. So if you see that this electron is being redirected, it will be caused because on the electromagnetic fields generated by this other particle. So because this is being redirected, it's emitting the beam stratum radiation. So using the Lorentz equation, we can obtain the first approximation of the beam surround radiation power, that it's as follow, where C1 it's a constant, I1 is the current of the beam interacting with the electromagnetic fields, and I2 is the current of the beam generating the electromagnetic fields. Another emitted radiation during the collisions is the synchrotron radiation. This is generated when a charged relativistic particle is deviated by interaction with an external magnetic field. Again, using the Lorentz force equation, one can calculate the first approximation of the synchrotron radiation power, which is as follows, where C0 is a constant and I1 is the current of the beam. Just to mention, because the beam surround radiation is generated because of the interaction of the two beams, this type of radiation comes from the interaction point. This means that this is the signal that the LABM wants to measure. Meanwhile, the synchrotron radiation comes from the magnets of the accelerator, and they are far away from the interaction point. So the synchrotron radiation is the background noise in the LABM data. The best way to understand how the LABM works is looking at its component. The LABM is divided into two sections. One of them is OHO and the other one is NICO. And each of these sections is divided into two paths. One is the up and one is down. Therefore, we have 4 optical paths: OHO up, OHO down, NICO up, and NICO down. Also, we have 4 beryllium mirrors inside the beam pipe, which help us to redirect the radiation from the collision. So this will be the interaction region. So the radiation will come on either directions, and then the beryllium mirrors will redirect this radiation to the optical paths. So this is the beam pipe. The radiation goes from the beam pipe through this small window, and the first thing it hits is the primary elbow, which is an aluminum box with a mirror inside that it's attached to 2 motors that allow us to move the mirror in 2 different directions. Then after the primary mirror, which is in this small part, the radiation goes through all the optical path, which is just a series of elbows and aluminum pipes, and inside each elbow there is a fixed mirror. At the end of the optical path, we have the optical box. And inside this box, first we have a Wollaston prism that divides the radiation into a part polarized in X and another part polarized in Y. Then we have a set of mirrors that redirect the radiation to the photomultipliers, which send the signals to the electronics and then store the data on the LABM computer. A simulation of the LABM was made using the GN4 tool. This simulation was made to understand the behavior of the background noise on the detector. GN4 was used because it let the user activate or deactivate different physics processes, which allowed us to fully study the background noise. The simulation was done using the actual measures of the LABM. For example, this is the HER beam pipe profile. Here we can see that we have meters, and here we have centimeters. So the beryllium mirror will be about 4 meters away from the interaction region in the x-axis, and about 4 centimeters in the y-axis. For each simulation, 2 particle bunches were created, one of 7 GeV electrons and one of 4 GeV positrons. These bunches were created with 1 million particles inside an ellipsoidal 1 cubic millimeter volume. Each bunch is emitted at the same time and passes through a magnetic field, which deviates the particle to the center of the pipe, generating synchrotron radiation. At the end, the simulation had a total of 84,000 events. So this will be the Nico side. This is the Ojo side, and the interaction region will be around this place. In here, we have the detectors at the end of the optical path. This uses we use the actual measures from the LEVM, which will be about 12 meters or something around that measure for each optical path. For the data analysis, sorry, at the end, we have a heat map that shows the photon hits on the detector. These photon hits are shown as radiation peaks in different parts of the detector. These are the results from the simulation. And we can see that there is a similar result on the LAVM scan. Even we have about similar structure. So for the data analysis, we start with a pedestal to remove the background noise generated by the electronics in the particle accelerator. To do a good pedestal, it is necessary to take data without beam, but the current of the beams are never zero. They oscillate around zero. This is why it was necessary to establish a maximum and a minimum on the beam currents to make a cut in the data. To find this maximum minimum, we use the HER and the LER beam current, and using the average and 3 sigmas, we obtained these current limits. And using this cut, we obtained the pedestal for each photomultiplier. After the pedestal was obtained, the next step is to do the scans. And this is done by moving the primary mirrors in both directions to obtain data of the radiation from all the effective area. A software developed by the LAVM group is used to move each motor remotely by steps. 2 data scans were done, one on the 2019 and the other one on the 2020. These are the results of the 2019 scans. It's a heat map that shows the normalized radiation power by step of each motor. We can see here that there is one motor and the other motor. This is a Ojo up scan. This is an Ojo down scan, and this is another Ojo up scan, but from a different region. Also, on each of these scans is marked the interesting points where we take data from them. So for the first Ojo up scan, we have 13 points, and we obtain data from these points. The same for Ojo down and the other scan of Ojo up. Now, these are the 2020 scans. We decided to use a measure point around the high radiation power peaks because we wanted to see the data from low and high radiation powers and compare each other. The first scan is from Ojo up. The second one is from Nico down, and the last two are different areas on Nico up. For the data analysis, we added the first approximation of the synchrotron and beam surround radiation power, obtaining this function where C0 and C1 are constant. I1 is the current of the beam interacting with the electromagnetic fields, and I2 is the current of the beam generating the electromagnetic fields. Normalizing this function with respect to the current I1, we have a two terms function. One is a constant, and the other one is a quadratic term. Fitting this function to the graphs of normalized power against the current, we could get two results: a constant fit, meaning that the point is only synchrotron radiation, and a quadratic fit, meaning that the point has beam surround radiation. This analysis was done on the 2019 data, and 3 types of fits were obtained. 6 points of the data had a quadratic negative fit, 4 points had a quadratic positive fit, and the rest of them had a constant fit. For the 2020 data, we only focus on the quadratic term parameter of the fit. Looking at each point, we could see that for Ojo up points around 29 and 42 have a parameter of at least 2 orders of magnitude bigger than the other points. Therefore, we took these points as quadratic positive fit and the others just as constants. And as you can see, the points 29 and 42 are in the high radiation power region. On Nico up, we can see the same behavior on points around 21 and 28. Meanwhile, on Nico down, all the points had a low quadratic parameter. Therefore, all the points have a constant fit. We can see that we have here that it's to the 10 to the minus 6. I don't know, perhaps it's not, doesn't matter. So for the conclusions, the simulation allowed us to understand how the synchrotron radiation behaves on the LABM detector. The simulation and the data scans gave us similar results, where we can see radiation peaks on some of the detectors, which we named as fake peaks because it doesn't have beam surround radiation, just like the one on Nico down from peak from the 2020 data. The 2019 data was taken in optimal conditions. Therefore, this data analysis allowed us to understand the behavior that data must follow. The 2020 data analysis allowed us to establish a methodology to differentiate synchrotron radiation points from beam surround radiation points by looking at the quadratic term parameter from the fit. In summary, thanks to the simulation, we could determine that the fake peaks are synchrotron radiation, which helped us to understand that most of the background noise comes from this effect. And a methodology was established to determine if the radiation is from synchrotron or beam surround effect. So for the work perspective, there is still some work to do. Some pieces of the LABM need to change to make it easy to install or manipulate the detector during operations. The beam surround effect needs to be added to the simulation, and finally, we need to correlate other beam monitor parameters with the data from the LABM. Thanks.
Thank you very much. Questions, Salvador?
I see no questions on streaming YouTube and no questions on, let me check. No, up to now.
Okay, so maybe we could thank you again and move to the next talk by Yusef Sarkis, please. Yusef?
Yeah.
Okay, you already unmuted. Thank you. Please start sharing your screen.
Okay, thank you. Let's see. If I'm sharing?
Yes, you are sharing, but
okay,
more than one slide at the same time.
Okay.
So if you can fit one slide on the screen.
Good.
Without going full screen.
Okay, oh, sorry.
Yeah, just to show one slide at a time would be perfect.
And if I can get something.
Okay, yeah, this way, thank you.
Okay, thank you for the invitation, for the presentation. So I'm going to talk about study of the ionization efficiency for the nuclear recalls, or is usually called for dark matter and seven searches quenching factor. So I'm going to give an update of the paper. Now this is a paper now. So I'm going to talk a little bit what is the importance of this quenching factor for dark matter and neutrino experiments. So I'm going to talk about this new model. It's beyond Linhart theory. So I'm going to talk about how to enhance, to improve the integral equation with binding energy, including binding energy, to explain a little bit how it can be solved numerically, and well, what are the results of the fits to the data, and well, to talk a little bit about an ansatz model that is simply to to plug or to understand or to use it. You want to use it for that analysis. Then the results and the conclusions. So for the dark matter direct experiments and seventh signals, generally these output signals entails detection of ionization produced by recalling larger ion following by a scattering event. We can see in the picture, this dark matter or neutrino, whatever you want to measure, extract or get into the material. Then what you see is the ionization signal. You don't see of course, the atomic movement, the direct atomic movement. You see the signal via some electronics as an output, but it's only the electronic signal. So generally this electronic excitation produced by a recovered ion. So it's typically smaller than produced by the electron of the same energy, because for the ion, some part of the energy transforms into heat or to atomic motion. This is what is called quenching, that quenching factor that change the unity, have this change of units of electron volt nuclear recoil to electron volt equivalent energy. So quenching factor is just a quotient of the ionization energy over the deposit and total deposit energy, nuclear recoil energy. Here, eta and epsilon bar epsilon r are in ionization energy and total recoil energy in some differential units. Okay, so there are special units that are used for these kind of calculations. So this model has a start with Linhart in 1963. He gave a parameterization for this quenching, but was only acceptable for relatively large energy, approximately bigger than 10 kiloelectron volts. So for recent measurements of quenching factor, for example, in silicon, it has been shown a clear deviation from Linhart formula below 4 keV. So the main problem from Linhart theory is that he neglected the binding energy term, and well, he ends with a simplified integral differential equation with this assumption, right, with no binding energy. So in this work, we're going to incorporate correctly this binding energy term into this basic integral equation and see how it changes, how it modifies this quenching factor, and is more tractable to lower energies. So let me explain you a little bit how it is important for example, dark matter and neutrino experiments. For example, for Connie, we can see in the left the spectrum rated with two quenching factors. Now, this Linhart is standard parameterization, and another quenching factor that is from data points and extrapolation from data points is called Chavarria, because it was the person who measured it. And we can see that there is almost a factor of 2 in the right-hand side with the beams of the expected rate. So it can change a little, very significant the result, in principle in low energy events. You want to see the 7s, this is only accessible to low energies. It's very important to have an appropriate theory or a confidence theory for this quenching factor. So also for dark matter, it's almost the same story. We see in the left the efficiency, the parameterized efficiency for wind detection. We can see that it's in electron volt electron equivalent energy, so it's dependent of the quenching factor. And of course, the limit, this band that we see, also proportional to this quantity. So for example, in this analysis for DAMIC, 0.6 kilogram limit, they say, for example, that this quenching factor has approximately a cutoff of 0.3 kiloelectron volts, more or less. No? It's an estimate that they use with their data. This one I want to mention because it will be important later. So, well, I think with this it's clear that this is a significant quantity to calibrate and to understand the low energy gradient for dark matter and neutrino experiments. So I'm going to talk about how is the model. So the model is for an homogeneous medium. So you have to first consider as a particle with a kinetic energy A, and this is given by a recalling particle, for example, dark matter or a neutrino, whatever. So this ion recoils with an energy ER, given by this incident particle. Then the ion excites in some way is the inner shells, from the lattice also, the lattice energy, is to spend energy to move, because we have to spend some energy to remove from the lattice. This is called the U. So we call it the restriction of atomic binding. So finally, the final energy of the ion is E. So it's the recall energy minus U. Minus this atomic binding, and then it repeats this process to all the over again. No, so this energy is dissipated in the medium. So what Linhart essentially considered at the beginning was an atomic movement. He called this quantity nu bar as an average. It was an additive quantity that consider this slowing down process generated by this cascade process equations. And well, he handled this equation that consider the incident particle, his first term, consider the incident particle. The second term consider the striking particle, the struck particle. And the last term consider the no interaction particle. And the last term here, in theory, consider also the contribution to electrons for atomic movement. That is, we will see that is neglectable because electrons is almost not massive. So all is done in the CM frame. So first, as I told you in the beginning, Linhart neglects the binding energy for all these computations. So this equation 1 is essentially the main integral equation. Now you can see it in the picture here. Now it's just look that I change nu bar for P bar, where P bar can be any additive physical quantity. So this is like the picture that they are encoded in the integral equation. So, and this is well repeated several times because it's a cascade event. So in order to compute a solution for new atomic movement, we have to make some approximations. In this case, 5. First of all, we're going to neglect the atomic movement from electrons because, as I told you, electrons is not massive also, and it's not in the relativistic regions. We are in low energy regions, so they're not very important. Energy transfer to ionized electrons is small compared to the transfer to recoil electrons also. So, and the effect of the electronic and atomic motion can be separable. So this is like a conservation of energy. We consider we have only electronic excitation and atomic movement. Well, also the recoil energy is small generally compared to the incident energy. And then, well, expands this the terms in the equation, in the main integral equation, to second order. This is the thing that I did as new, and including the binding energy. So there is a way to handle all this using this approximation and the integral equation. You can get to the simplified, as I call it, integral equation with binding energy. Now we have also to consider the electronic stopping power that is proportional to velocity with a constant. This is essentially also called Linhart theory or Lenz-Jensen theory. And some nuclear stopping. A cross-section for the nuclear stopping is considered also, for example, in this case, Thomas Fermi, for example, would be another potential, etc. So you can see that the stopping power is in the left-hand hand side of the equation, and the nuclear stopping is in the right hand side. So this equation can be solved numerically from F bar epsilon greater than or equal for U. So you can easily see that there is a threshold in epsilon equal to U. From here, the integral. You put epsilon U, the integral is 0. So this equation predicts this threshold in the energy of U. If we translate it to the recall energy, is 2 times U. Because remember, recall energy is the free energy plus U. So this equation admits a solution with a kink, a discontinuity of the first derivative in this point. So the idea is that, well, is to use a shooting method. I put you here in the more or less a very brief summary. So we have a boundary condition. The boundary condition is a second derivative at infinity has to be 0. So the idea is to match the right-hand side at epsilon equal to U with the left-hand side, because that's the cutoff prediction. And from the left-hand side, we get a relation. This above, this below relation. And well, with that relation, we have like initial conditions. And we have to guess these initial conditions until we reach the boundary condition. This is called the shooting method. It's like a blind method. You can see in the right-hand side, all these tries until we get the solution that is a red curve. So this is also called the Monte Carlo method too. So we use this method to solve the equation. And then, for example, we apply it for silicon and germanium. In this case, we made a fit for silicon data over our parameter region of binding energy and the stopping power or the K. Okay, so we compute the chi-square per degree of freedom. We see that there's a lot of spread in the data. Most of the data is not consistent, some energies. So we cannot expect a very good fit, but well, it gives us an idea. And I can get, for example, the minimum chi-square here is 8.7, and with that I get the binding energy and the electronic stopping. So the binding energy is interesting, that is consistent with the binding energy computed for the silicon, for example, of the order of 100 electron volts. Consider also the dislocation energy or the Frenkel per energy, and the electron hole per energy is approximately 150. Okay. Is the result that I get in this field. For germanium, it's also almost a similar procedure. I get a binding energy of the order of 20 electron volts. So it's very consistent with this table. So this binding energy finally is also incorporates in some sense the micro effect. Then, well, as we can see, this procedure could be complicated. So in order to get like an approximate solution, we get this ansatz that the idea is to lessen the ionization contribution of the electronic stopping power by a proportional factor of the same stopping power and a constant. This model works finally well. You can see that in the idea of this ansatz is that in the low energy part, it has to be linear. Okay, that's what our theory predicts. And in the high energy, it has to tend to linear. Okay, so this corrected curve is what is the ansatz does. As you can see, it's an approximate solution, not exactly. So I will show you the results here. For germanium, here is the model, is the ansatz here, and the numeric is all this solution of the integral differential equation. We can see that it differs a little bit in the low energy region, for example, for germanium. But we can see that the curve path describes well the data available for germanium up to the lower energy. Also the ansatz, this error band just approximately cover the data fluctuation. As I told you, it's not very consistent. So this is what we have for the moment. Also for silicon, you can see, for example, Linhart here in blue is very different at low energies from the data on Chicago, or Chavarria is the same experiment. So our model gives a good prediction in this region, better than Linhart, and in the high energy regions, approximately very well to Linhart. Okay, I found a K value of 0.161 that is very consistent what is expected. So finally, the conclusion is that we found an appropriate form to solve this basic differential equation for first principles. We describing the energy given to atomic motion and considering the binding energy. We are the first work that consider this term. We see that for germanium, the data described very well by our model. For silicon, we see that our binding energy is on the range of 100 and 250. It's interesting to see that it's consistent with the dynamic data estimates. It's a cutoff of 0.3 kiloelectron volts or 300 electron volts. So we think it's fine. So also the predict, we think that this cutoff is a little bit larger even. So we think that it has to be in the order of range of the location energy of about 40 electron volts, 36 more or less. And well, will be a more reasonable physical cutoff. Of course, this model can be expanded. Consider, for example, energy variable binding energy, or a modified expression for the electronic stopping power for low energies. There is a lot of literature of that. And where we are doing that in the moment is work in progress. So that's what I have. Thank you.
Thank you very much, Joseph. Questions for him, Salvador?
No, I don't see questions on YouTube. Let me check in somebody's raising. No, we don't have any questions up to now.
Okay, so are you working directly besides DAMIC with other collaborations to implement this in the data analysis?
Well, also in Connie too. Yes, Connie.
Yeah,
I'm
DAMIC
working also in Connie. DAMIC Connie, yes.
Okay.
Even now Connie is making a new paper, and they're going to use this quenching factor.
Oh, very good. Okay. Any last moment question? No, Salvador?
No, I just have some announcement, but no.
Okay. Okay, so for the moment, we thank a lot again, Joseph, and go to the last talk in this session that will be given by Leon Manuel Garcia de la Vega, speaking on Dirac neutrino masses and axion plus wind dark matter from Peccei-Quinn symmetry. Please unmute your microphone if you didn't do it yet.
Hello, can you hear me?
We can hear you. Yeah.
Okay.
And can you share your screen, please?
Yes.
Okay, very good. Whenever you want.
Okay. Hello, everybody. I'm going to talk about a framework for Dirac neutrino masses with axions and wind dark matter. So basically, what we want to aim is to use the Peccei-Quinn symmetry to describe Dirac neutrino masses and a mixed model of them. So our motivation is that we know that the standard model is incomplete. We know the low energy gauge groups and the pattern of symmetry breaking, which gives masses for the fermions, the quarks, and the charged leptons. But we know there is more to this picture. There are several problems that the standard model cannot address. one of these problems is that we know from cosmological and astrophysical observations the existence of a non-baryonic neutral component of matter, which is actually a quarter of the matter energy content of the universe today. There are several ways of explaining this component of matter, several models, from WIMPs to axions, or even massive astronomical objects. And there are also non high energy solutions to these problems, but we are going to focus on the WIMPs and axions solution. There is also another aesthetic problem of the standard model, which is called the strong CP problem, which consists in the non-observation of a CP violating theta term of QCD. To the QCD Lagrangian, we can add this term, which respects all the symmetries of the standard model. And this term leads to an electric dipole moment for the neutron, which is of this order, 3 times 10 to the minus 16 times theta e centimeters. And this quantity is very well measured to be less than 10 to the minus 26 e centimeters. So to obtain this very small value, we would need to have a theta term to be less than 10 to the minus 10. So the question is, how can we obtain such a small number from a term that is not constrained by any symmetry? So a solution is to add a symmetry to the theory, which is called the Péchet-Quinn symmetry. Another shortcoming of the standard model is the existence of non-zero neutrino masses. From oscillation experiments, we know that neutrino masses exist. At least 2 of the 3 active neutrinos have mass eigenstates, non-zero mass eigenstates. So, but from other observations, we know that the scale of these masses is very small. From beta decay, we know that this must be smaller than 1.1 eV. And from cosmology, we know that the sum of the masses must be smaller than 0.1 EVs. So a natural question is, why is this scale so much more small than the electroweak symmetry breaking scale, which is a mechanism that gives masses to the rest of the fermions? Another question that the standard model doesn't address is whether neutrinos are Dirac or Majorana fermions. One way of looking at neutrinos is if they're Majorana particles. You have lepton number violating mass terms, which lead to processes where the lepton number is violated in 2 units, such as neutrinoless double beta decay, which is this process. And this is the process that is measured by Kamlansen. So the standard model symmetries allow for Weinberg dimension 5 operators to give Majorana masses to the neutrinos. There are 3 level ways of obtaining this operator, which are called the CISOs, type 1, type 2, and type 3. And through these processes, we obtain masses which are proportional to the square of the electroweak symmetry breaking, which means that we need to invoke a much larger mass of the mediators to explain the smallness of the neutrino masses. So another way of obtaining neutrino masses and explaining their smallness is through loop level models. There are a lot of loop level models. Some of the most basic ones are the scotogenic, the C and the C-Babu. And from this, scotogenic is curious because the additional symmetries that forbid 3-level masses gives rise to dark matter candidates. We also have the possibility that the neutrinos are Dirac particles. We can obtain this by forbidding the Majorana terms by some symmetry and only having Dirac type masses. This would imply a lepton number conservation and a non-observation of lepton violating processes such as neutrinoless double beta decay. We can forbid this symmetry by using abelian or non-abelian symmetries, continuous or discrete symmetries. In this framework, we can also explain the smallness by loop suppressions, obtaining this operator as an effective operator from higher order operators. Here we will use the Pechequin symmetry to forbid the Majorana neutrino mass terms. So the idea of the Pechequin symmetry is that it absorbs the theta term from the QCD Lagrangian, solving the strong CP problem, explaining the smallness of this operator. This breaking of a global symmetry predicts the existence of a pseudo-Namdu Goldstone boson, which is called the axion. And we have to introduce a new energy scale to the model, which is called the Pechequin breaking scale, which is denoted by Fa. So there are three main popular models for this Pechequin symmetry, which is the Pechequin-Wilczek-Weinberg, which is the first form this symmetry was made, which is that the axion is a part of an SU2 doublet, but the smallness of this Pechequin breaking scale leads to an exclusion by pion observables. So by making the idea is that if you make this scale very large, the axion decouples from nucleons and hadrons. So there are the other two ways to do this is by coupling this axion to heavy vector-like quarks or to Higgs doublets, while being a Higgs singlet. This last option is called the VFSC, and this is the framework in which we are working. In these kind of models, you have a 2 Higgs doublet model with a standard model singlet, which is charged under this global symmetry. You have two ways of coupling the singlet to the Higgs doublets, which is through a trilinear or a quartic term. And we remember that in these 2 Higgs doublet models, these Higgs doublets give mass to fermions in a way similar to the standard model. And for neutrino masses, we can use traditional mechanisms, which we can consider as some form of extensions of the seesaw. And these ideas have been here for long. This is a paper by Peche and others from 1986, in which they use an extended Weinberg operator with the Pechequin symmetry to obtain Majorana neutrinos. We can use Pechequin charge assignments to forbid Majorana terms. That's the idea for Pechequin Dirac neutrinos. In this work by Peinado and Valle and others, they give these charges to the standard model particles and to the Higgs doublets and to the singlet. And under these charges, the Majorana mass terms for these neutrinos is forbidden to all levels, to all perturbation orders. So once you have this, you need to complete the UV of the Weinberg operator. One way to do this is by introducing the type 1 CISO with an exotic new R charge. And under this operator is a Pechequin invariant, so you lead to after Pechequin breaking, you lead to a Majorana mass, which is proportional to the Pechequin breaking scale. So you have a large suppression by you need a large suppression by the mediators to obtain the correct neutrino masses. So because of this form of the equation, you have a complementarity between the axion observables and the neutrino masses in the axion photon coupling and the neutrino mass plane, which basically means that in these models, the neutrino mass measurements are going to be excluding you from below, while the axion observables exclude your model by above. So what we did was extend this idea. We start with the same framework for a trilinear coupling of the axion to the Higgs doublets and the right-handed neutrino. So we have already seen that this choice of charges leads to forbidding the Majorana mass terms at all levels of perturbation. So if you complete the UV operator with a Higgs doublet with a charge 6, you obtain a type 2 kind of Dirac CISO, in which your neutrino mass that you obtain is as well proportional to the Pechequin breaking scale, but is inverse to the square of the mediator mass. And you can also express this mass as being dependent on the scalar mixing angle, which in these invisible axion models, you need it to be very small.
5 minutes.
Okay. In this framework, you can use the Catherine direct measurements or the cosmological measurements of the neutrino mass to exclude this combination of parameters, the trilinear couplings times the Yukawa. And we also have we can complete this operator with another set of particles. Namely, we can add a Higgs doublet, a Higgs singlet, and 2 fermions, which transform in this way under the Pechequin symmetry. And after the breaking of this symmetry, we obtain a residual C2 symmetry, which is similar to the scotogenic, but if we look closely, there is some weird negative charges for standard model particles, which we will address later. But the idea is that this pattern of symmetry breaking, in which the additional doublet and singlet do not get vacuum expectation value, leads to the generation of Dirac neutrino masses through a one-loop mechanism similar to the scotogenic. In this model, we have mixing in the scalar sector of 2 blocks, the Higgs doublets and the singlet containing the axion mix among themselves, as in the standard DFSC mechanism, but we also have the two new scalar particles mixing among themselves. And this seclusion of these two sectors gives rise to the possibility of having dark matter. So after this breaking of the Peché-Quinn symmetry, we have a C2 symmetry in which these are the charges. Neutrino masses are obtained as well through this loop diagram, in which we see that, again, the neutrino masses are proportional to the Peché-Quinn breaking scale, to the electroweak breaking scale, and inversely proportional to the square of the mediator masses, but we also have a loop suppression factor. So the particles running inside the loop are dark matter candidates, which means we have the possibility of scalar dark matter or fermion dark matter. In the case of fermion dark matter, we have a picture that is similar to the scotogenic model. We have GeV, hundreds of GeV scale for the dark matter candidate. And in the case of the scalar, we have the same, but we have a different equation for the masses. The WIMP stability of the N and S of the loop is a mixed mechanism of Lorentz and the C2. We have an interplay between these two symmetries to obtain WIMP stability. And finally, the axion is a good dark matter candidate. So in this picture, we have two components of dark matter: the axion plus the lightest particle inside the loop, which, as I explained, could be a fermion or a scalar. And in the case of the scalar, we have it's a mixture of a doublet and a singlet. We studied two limiting cases in which you have mostly 1 minute singlet, yes, which is very similar to the inner singlet. And you also have a scheme that is very similar to the inner doublet model, which are widely studied in the literature. And in the fermion case, you have a picture that is very similar to the Majorana scotogenic model, but we have the presence of a right-handed neutrino mode for annihilation of dark matter, which relaxes the bounds that are very tightly constrained for the scotogenic model. So to summarize, the Peché-Quinn symmetry can provide a framework for neutrinos and dark matter. The Peché-Quinn symmetry can lead to the Diracness of neutrinos, and it can also result in a multi-component dark matter scheme. And through this symmetry, we can, in this scheme, we can relate axion phenomenology with neutrino phenomenology and WIMP dark matter phenomenology.
Okay, thank you very much, Leon. Are there questions to him, Salvador? Already?
No, I don't see questions. Let me check on. I don't know. No questions.
Maybe I can.
Yes, we have a question from Wolby. Yes, go ahead, Wolby. You can ask.
Yes. If I understand you correctly, you want to introduce a charge -5 for the right-handed neutrino. I assume this is electric charge. I'm puzzled, is this compatible with gauge anomaly cancellation?
This symmetry is not gauged. This is a global symmetry.
An electric charge is a coupling to an electric gauge symmetry, right?
This charge is Peché-Quinn symmetry. It's a charge of the global U1 Peché-Quinn symmetry.
Yeah, but charge means that you couple to a gauge field, right?
It's the transformation under this global symmetry. It's not a gauge symmetry.
Okay.
May I ask a short question?
Yes.
Yeah. Okay, so can you summarize for us your preferred solution, especially the masses and couplings involved?
Okay. For
your last discussion,
for this, we have in the mixed dark matter scheme, we have phenomenology that is similar to the scotogenic model, the Majorana scotogenic model, in which you have WIMP dark matter of the order of hundreds of GeVs. And we also have made use of a standard scale for the Pechet-Quinn breaking of 10 to the 12 GeVs to obtain the neutrino masses of the order of 1 electron volt, which is the bound from Catherine.
Okay, thank you. Are there other questions, Salvador?
Yes, if there are no more questions, I will just give an announcement.
Thank you.
Okay, so thank you very much, everybody, for your participation. I will interrupt your presentation now. So I just want to remind everybody that we have this afternoon this poster session. So you can see we have already 9 posters, even though it's at 4 p.m. So please feel free to join. The link is on our overview of our Indico page. Please, you can join and ask questions to each of the presenters. And we have a procedure we will ask for a request for the best poster presentation. There is already people asking for this. Questions to everybody. So please feel free. This is a new way we are presenting the poster. There is a YouTube video of up to 10 minutes. And you can ask on the chat any question. Please feel free to participate. And I think this is so everything I wanted to say. Pablo. So this ends our first part. I will stop the streaming. We will resume at 2:20. That's correct. Yes. So we thank you, everybody. We apologize for being a little bit tight for the schedule, but we are very good in time. Thank you very much, everybody, for this, for all your participations. Thank you. Thank you. I would like to say that we have up to 56 people, up to 84 people in total, considering also the YouTube at one time. Thank you. Enjoy your meal. Bye.